Уважаемые коллеги, добрый день. Я сначала по-русски скажу. Мы начинаем нашу сессию, совмещенную Луна и Меркурий. Вот, начнем мы с сессии Меркурий. Рабочий язык конференции английский, поэтому дальше мы все будем говорить по-английски. So, dear colleagues, welcome to our next day of our conference, the Moon and Mercury session, and we start from the Mercury session. And the first speaker will be Alexander Kozyrev, and the title of his presentation is MGNS Experiment Science Investigation during cruise to Mercury on board ESA Bepi Colombo mission. So, Alexander, please go to the presentation.
My report will describe our current status of the MGNS instruments. MGNS instruments is a mercury gamma ray neutron spectrometer which installed on the NPO spacecraft of the Bepi Colombo missions. These instruments have the two parts. One part is can detect the neutrons by the helium propulsion 3 counters and the steel beam crystals, and also MGNS instrument consists of the gamma ray spectrometer based on the cerium bromide 3 crystals. And we can detect the neutron from the thermal energy up to high energy above the 7, 8 and up to 10 maybe, and the gamma rays from the about 200 kV up to 10 MeV with energy resolution about 6% for cesium lines. The main goal of the science goal of the MGNS instruments is detect the neutrons and the gamma rays from the surface of Mercury, and by use this data create the map of the global distribution of the main elements on the surface of the Mercury, and also detect the possible hydrogen in the polar regions, which can base it in the permanently shadow regions, and detect the volatile element also in the polar regions of the Mercury. And the top figure shows the MGNS instruments, and also figure shows the installation's place of the MGNS instruments on board of the NPO spacecraft. The main stage of the Bepi Colombo missions is the after launch is the cruise, which consists of the set of the flybys, one in Earth, 2 by Venus, and 6 flybys in Mercury. This is a long way to the Mercury inside to the solar systems, and the current time of the beginning science orbital stage is the beginning of the 2027 year. And now we perform 6 Mercury flybys, and before the orbit insertion, we will perform additional two Mercury flybys. In cruise configurations, Bepi Colombo missions consist three spacecraft. The top of one is the MEO, called by MMO, Mercury Magnetospheric Orbiters. This one, this is the Mercury Polar Orbital, and MGNS instruments integrated here. And also this is a Mercury Transfer module. This module helps the Bepi Colombo to move to the inside of the solar system to the Mercury. And during the cruise, MGNS instruments operated practically continuous, with except of the period when the some work with the spacecraft performed. And during the cruise, we measured the flux of the gamma rays and the neutrons. By using the data, we detect the solar flare. For example, in this figure show the count rates in the long-term profiles of the gamma rays, and strong peak correspond to the solar flare. And also by use the gamma ray data, also we perform the localization of the gamma ray burst. And also by using this gamma rays data, we perform the spectroscopy tasks. We measured the gamma ray spectrum, which generated by the gamma ray from the spacecraft body, and this spectra, which was created by use of the data from the fourth year, not for the third year of the missions, and we detect some elements which correspond to the spacecraft body. And also we compare this spectrum with the data from the GRS instruments on board the Messenger. This figure shows the comparison between the two spectra, between the two data from MGNS and from the GRS instruments. And the blue line corresponds to the original spectra of the GRS spectrometer based on the germanium crystals, and that has very good resolutions. And the green line corresponds to the GRS spectrum, which resolutions close to the MGNS instruments, and we can compare the green line from GRS instruments and the yellow line from the MGNS instruments, and we have the good correspondence of this peak, which detected by GRS and which detected by MGNS. And we have some part of the spectra. For example, this line, which will detect only MGNS instrument, because this is line from the cerium crystals from our detectors. Also, we have in the GRS line, which detected only in GRS germanium detector, because this corresponds to the germanium elements. From all another elements, we detected by both instruments, because we have for example, aluminium, magnesium. We have this element in body of the both spacecraft. Also, the next slides I will present our results based on the flybys of the Mercury. The next three slides, which describe of the condition of the Mercury flybys. This slide show of the map distribution of these flybys on the Mercury surface. We performed the four flybys of the Mercury. This is lines. This is just trajectories with time intervals plus minus 6 minutes. And 4 flyby also performed. Fifth flybys it's skipped from this map because this flyby will perform it on the high altitude about 40,000 kilometers. It's not interesting for MGNS instruments. And for next interesting flybys, next is the 6 flybys with this altitude above the 300 kilometers, and we will perform it in the beginning of the next year. Also, this slide shows the speed of the spacecraft and the altitude time profiles for all flybys, for Mercury and the second Venus flybys, and that means that we have the different speed of the spacecraft in the closest approach. This line, this is a close approach, and we have the very different speed of the spacecraft, and it is necessary taken into account for the numerical simulations in context of the neutrons, calculations of flux of neutrons, and also we can take into account the different distance as functions of the time. It is also necessary to take into account to data deconvolutions. Also, this figure shows the orientation of the spacecraft for the flybys. The line on the left figure corresponds to the direction from the MGNS instruments to the center of the Mercury for all flybys, and for one Venus and the 3 Mercury flybys, MGNS instruments will open to the surface of the Mercury, and for last flyby, 4th flyby, this line, MGNS instrument was closed by the spacecraft body, and the right figure describes the structure of the spacecraft body. We will have some tanks with fuel between the MGNS and the Mercury, and also this is necessary. This take into account when we perform the numerical simulations of the data. This figure shows the time profiles for neutrons detector sensor of fast neutrons, and perform it for all Mercury flybys. The top figure, this is the raw data from the instruments, just level of background, and the peak correspond to the flybys, and for this line corresponds the background of the neutrons, which take into account close the Mercury body from the galactic cosmic rays, and this figure, this is the neutron signals without the background, and this peak correspond to the neutrons from the only from the Mercury surface. And for all our flybys, we can show that in the maximum peak we have decrease of the counter rate and the flux from the neutrons, and this occur because we have the decrease of the galactic cosmic rays. Also, this the same figure. This is the raw signal from the detector, and the background subtracted signals for gamma ray spectrometers of the MGNS instruments. And also we have the raw signals, the background, and the background subtracted signals which peak correspond to the gamma ray flux only from the surface of the Mercury, and decrease of the peaks, maximum count rate in the peaks, or due to decrease of the count rate because of decrease of the galactic cosmic rays. And this figure, next slide, show long-term profiles of the neutron detectors right and the gamma ray detectors left of the counter normalized on the beginning of the missions, and this trend corresponds to the galactic cosmic rays, and we use this data from gamma and from neutron separately to normalize our data to the the same count rates, and the lines this corresponds to the time moments of the flybys from the for Mercury and one for Venus flybys. And the next slide just show the neutron signals from all our neutron counters, neutron detectors, and these time profiles taken into account the background subtracted, and also with time profiles take into account the normalization for the galactic cosmic rays. And we have the just the last flybys, number 4. This is the right figure, corresponds to some difference from the another flybys time profiles. This difference because they have the different orientations for these flybys. And we have the another difference between one profiles to another profiles from all our flybys. Also, this next slide corresponds show the time profiles of the gamma ray signal from the Mercury, and the left figure show the time profiles of the gamma ray fluxes, and we have the difference between counter rate in the peak, and we have difference in the last flyby from another flyby because we have the effect of the orientations. And the right figure, this is the count rate flux of the gamma rate as function of the distance from the Mercury surface, and we have the no difference one count rate one profile to another profile from all our flybys, with exception of the last one because we have the effect of the orientations. And the right figure I show the intervals plus minus 1,000 kilometers. We use this interval to analyze the gamma ray spectra from the Mercury surface, and the left figure show the gamma ray spectrum. This is the raw data as function of the spectra in the amplitude channels, and the right, this is the same spectra for our flybys in the calibrated by energy. And
Саша, 1 минута осталась.
okay. And next slide correspond to the summation spectrum, red wine for all our flybys, signal plus background, and blue one is just background, and the right spectra just subtracted background signal from the Mercury surface. And the next slide, this is the same spectra by summation by the same channels, energetic channels, and we can show the 3 gamma ray lines which we detected from the surface of the Mercury. Left one is the potassium line, and the next one is this very strong line, the silicium. And right one, this line corresponds to the 3 elements, hydrogen, aluminium, and here. 3 lines for the right line on this spectra, and we have the good significance on this line. We have about the 8 sigma for the silicium line, and also we have the correlations and consistency, the aluminum to silicium and Ser to silicium. We have the correspondence to the messengers data if we comparisons with MGNS data. So this is the conclusion slide. I can conclude we have the successful perform the background measurement during the cruise, and we detect a lot of gamma ray bursts in the solar flare during the cruise. We perform the special sessions of the measurements of the gamma and the neutrons from the flybys in the Mercury and in the Venus. And during flybys of the Mercury, we detect this intense flux of the neutrons and the gamma ray lines, and also we detect the gamma ray lines from the Mercury surface, which corresponds to the mains elements, and we just use the data accumulated on the short time intervals. We use about the 10 or 15 minutes for just one flybys, and during the mapping stage we will create the global distribution of this element on the Mercury of the surface of Mercury. That's all. Thank you very much.
Cool. Thank you very much. So please, questions. I have some short question for myself. I know that the cruise to Mercury is delayed during the spacecraft problem. So could you tell the date of the arrival, and then you plan to start global mapping?
The orbit insertions and the arrival to the Mercury shifted to the right. The last data to the beginning of the mapping stage is the beginning end of the 2026. We will the insertion to the Mercury orbits. At the beginning 2027 we will start the mapping phase and the science phase of the missions.
Okay, thank you. Thank you again. So we need to move to the next talk. The title of the next talk: recent geological activity on Mercury. I apologize for the non-correct pronounce of the family name. It will be presented by John Xiao. So please proceed.
Thank you. Can you hear me well?
Yes.
Okay. So I'm sharing my screen. You can see my screen. So can you see the presentation?
Yes, it's good.
Okay. Yes, you can. Okay. Okay, cool. Thank you. Thank you for the introduce, your pronunciation. Oh, my name is correct. Thank you. So today it's very happy for me to share our research progress about recent geological processes on Mercury on the Moscow Symposium. I should apologize first that due to the teaching duties, I cannot participate the symposium in person, but I'm looking forward very much in the future that we can have combined the Sino and the Russia planetary science symposium in the future. Okay, so I will have a brief introduction about the general geological, geochemistry, and geophysical properties of Mercury. So Mercury is the innermost planet in our solar system. So here shows the global topography and also morphology of the planet. So the first appearance suggests that this planet is pretty different from the Moon. Also, they have comparable sizes. So there's no global dichotomy of Mercury. We can see plains that have fewer impact craters, and we can see patches of highland areas that were more intensively bombarded. So the general morphology of the surface of Mercury can be divided into plains, impact craters, and also big tectonic features, which we can see on the screen. The linear and orbit features, they are all tectonic structures. So in terms of surface color, here shows the global mosaic of Mercury at 750 nanometer reflectances. We can see that the color difference, or say the albedo difference of different units on the surface of Mercury are small. We can see relatively bright areas, the northern areas, that is less intensively separated, and we can see huge impact basins that were flooded by higher reflectance materials. And we can also see impact rays suggesting that space weathering also happens on this planet. So if we stretch the color, or say if we stretch the reflectance at different bands to compose a false color image. So here shows a PCA, false color principal component analysis, to stretch the different color properties in visible to near infrared wavelengths. We can clearly see that the surface have different colors. The plane materials on this false color composite appears to be brighter, and also the spectral slope is steeper, so it looks like orange. And the majority parts of the planets have much lower reflectances. That is coded as the blue unit here. They have a specific definition called the low reflectance material. So in a very dark planets, that we can still see geological units that perhaps have different compositions. Okay, so in terms of internal structures, we put the internal structure of Mercury at the same scale with that of the Earth. Immediately we can see that the internal structure of Mercury is more or less like an egg. So it has a very thin crust. The average crust thickness is about 44 kilometers. Besides that is 100 kilometer thick mantle, and the majority portion of the planet interior is a core. So this is the best resolved structure of Mercury. It should have a liquid outer core that have driven the global dipole, the convection of the outer core, fluid core has formed the global dipole magnetic field. So this is the internal structure. And there are global gravity data for Mercury. So the highest harmonic degree is 120, and this gravity model has a better resolution to the northern hemisphere because of the highly elliptical orbit of Messenger. So at the northern planet, we can also see features in the Bogey gravity map, shown in the middle, that a lot of large impact basins, such as the Chloris Basin and the nearby basins, the interiors also feature positive Vogel gravity anomaly, suggesting that these large impact basins appear similar with those on the Moon, that we have mantle plugs that were caused by giant impacts on the planets. In terms of crustal thickness, we can see that the crustal thickness is thinner at large areas of volcanic plains to the north, and the basin interiors also feature smaller crustal thickness here. So this is the basic geophysical background of the planets. In terms of composition, the X-ray spectrometer and the gamma neutron spectrometer of Mercury has revealed very different composition compared to the other planets. So first of all, if we compare the potassium to thorium ratio of Mercury's surface, and we compare that to the other terrestrial body and also the Moon, we can see that Mercury seems to have a much higher internal volatiles compared with the other terrestrial planets. It's even comparable or higher than that of Mars. So this is one of the biggest findings in terms of geochemistry during the Messenger observation. So Mercury has a surface gravity that is comparable with that of Mars, but its size is only slightly larger than the Moon. So that suggests we may have a lot of iron in the interior of Mercury. And also the surface reflectances, average surface reflectance of Mercury is much lower than that of the Moon, suggesting that we might have some iron bearing opaque phases on the surface of Mercury. So that is one of the anticipated results before observations. When Messenger went into orbit, the reflectance spectra at visible to near infrared obtained by the two instruments. One is MDIS, it's called the Mercury Dual Imaging System. Another one is MASCS. So this is a multiple channel reflectance spectrometer. So the two data sets returned confirmed earlier observations by Marina 10 back to 1970s that surface material of Mercury basically makes a clear observation band at 1 micron. So such minerals containing iron 2+, they should be very abundant on all the terrestrial planets, especially the Moon, but we do not see feature on the surface of Mercury. So one big question for these two observations is that the interior of Mercury contains a lot of volatiles. The bulk composition contains a lot of iron, but the surface material generally makes the ferric iron. So what will be the opaque phases? What causes the surface no reflectance of Mercury? That's one of the biggest questions to be resolved for Mercury as well. Okay, so in terms of other major compositions, observation from a XRS and GNRS of Messenger has observed also very different composition compared to the other planets. So in general, the surface composition, the magnesium content of Mercury is very, very high. So this shows a magnesium and a silicon ratio. And we can see that they get a ratio as high as over 0.8% in several large areas. So this area particularly has a dimension of 3,000 kilometers. This is called the high magnesium region. And the other regions also contains a lot of magnesium as well. And also the sulfur content on the surface of Mercury is also very high. So on average, they can contain up to about 4 weight % of sulfur. So this content of sulfur is actually much higher than the Earth, and also Venus is also almost comparable with that on Mars. Okay, so this is the general composition of the different geochemical units on surface of Mercury. And another finding is that the reflectances of geological units on Mercury are not strictly correlated with the content of elements, such as iron and also calcium. So there's no strict correlation between the two. That is a big trouble for us to resolve the possible composition of different materials on the surface. Okay, so in terms of geological evolution, at a scale of 1 to 25 million, geologists has mapped the different geological units by referring to the stratigraphic system of the Moon. So by referring to key impact structures on the surface of Mercury, such as Tolstoy Basin, Chloris Basin, Masson crater, and Kuiper crater on the surface, the geological system, the stratigraphic system of Mercury can be divided into the 5 episodes. So that basically follows the definition of stratigraphic system on the Moon. And also the anchor point in terms of absolute model age that were derived from crater statistics also referred to those on the Moon. But as we can see here that the absolute model ages for different geological periods are systematically different according to different production and also chronology functions employed for Mercury. However, based on the cross-cutting relationship and also the size frequency distribution of impact craters on the surface, different geological units belong to different stratigraphic epochs are stretched. Here we can see that we have basically have a global geological map at large scales. So from this large scale geological map, we can divide the geological evolution of these planets into different episodes. So the first one is the earliest period is the Precolostoic period. It's occurred earlier than 4.1 or 3.9 billion years, depending on the lunar chronology function, Mercury chronology functions we employed. So the evolution of the different episodes can be summarized into a pretty easy story that the planets was initially heavily bombarded, and then there was global or regional resurfacing processes, and then a lot of impact craters were accumulated again, and then there were smaller impacts that were continued to the present day. So that's the general geological evolution of the planet. The earliest geological evidence comes from the most heavily cratered area on the surface of the planet. So the upper left panel shows a crater density map for the global Mercury. That is for craters larger than 25 kilometers per million square kilometers. That we can see two large areas have the highest crater density. If we compare the highest crater density with the crater density of the large impact basins, it's evident that the cumulative crater density of the large impact basins are comparable with the most densely cratered area, suggesting that the basin forming epoch is comparable with the most ancient terrain. So therefore, earlier studies suggest that during the basin forming epoch on the surface of Mercury, there may be a global resurfacing events that have erased earlier geological records. And this resurfacing event might have caused the intercrater plains that cover about 30% of the global planets. So this is one of the earliest geological records that is still preserved on the surface of Mercury. And also the highly interested area, the high magnesium terrain here, it has a very high content of magnesium. If we look inside this region using the color map, we can see that this area also composed of different color units. And some of the bright areas were excavated high reflectance materials, and other areas were pyroclast deposits on the surface. So it has been hypothesized that this terrain, the high magnesium terrain, should be the oldest area, and it may be related with special dynamo of Mercury in this particular region, so that have caused volcanism with different composition, with higher magnesium content in the volcanic product. So the recent usage of impact craters as probes to see what's the material that were exposed and what's the composition of the impact ejector with different sizes. So using this method, we can reconstruct the subsurface structure of the entire high magnesium region. It suggests that the high magnesium region seems to have stratiated layers with different color at various depths. So this picture gives us an interpretation that the high magnesium terrain may be consistent with a very ancient large impact basin, and the subsequent volcanic resurfacing from different depths of the mantle, which is heterogeneous in terms of composition, can cause the observed different color and also high magnesium ratio. So that's one of the interpretation. So are there any ongoing or recent geological processes on the surface of Mercury? So of course we have new impacts. So using the temporal imaging method, that is, we compare two images or different images obtained for a given spot but at different time to see the ratio or the short-term changes on the surface. We can see that features short-term changes that are consistent with being recent impacts. However, if we estimate the size of impacts within this region to the source crater, and we plot the distribution, size frequency distribution of the observed new impacts on the surface, and we compared that to the predicted production density of impact craters on the surface, we can see that the observed crater production is orders of magnitude higher than the canonical chronology models. So there are two interpretations for this. One is that the impact flux on Mercury may be much higher than we thought. Another thing is that, you know, the estimation for the size of impact craters within the spot is much larger than we think. So so that means the observed seismic distribution can be systematically shifted to the lower diameter range. So that's another interpretation for the two. In terms of endogenic geological activity, before the MESSENGER mission was inserted into the orbit about Mercury back to 2011, scientists believe that. Okay, scientists believe that Mercury should be like the Moon. The internal geological activity has been ceased. So with MESSENGER data, we can see that a lot of young plants that we have introduced, they have less crater density. If we use morphological evidence of volcanic wall impact ejecta, similar to night plants on the Moon, we can divide the smooth plants into different categories. Yeah, we identified volcanic smooth plants, and then we determine the size frequency distribution on the young plants. So those plants cover about 27% of the planet, and their size frequency distribution seems to point to a pretty unified crater density that gave us a model age about 3.7 minus or plus 200 million years. So the last episodes of effusive volcanism on the surface of Mercury seems to have a pretty restricted eruption window within about 400 million years. And this period is actually coincidence with the formation of large impact basins such as Flores and Rembrandt. And these large impact basins have a model age of about 3.8 or 3.7 billion years. So the two epochs seems to be consistent with each other, indicating that you know, large impact basins might have triggered a catastrophic near global distribution of effusive volcanism on the planet. So that's the latest, youngest volcanic plants on the surface of Mercury. Are there only evidence of more recent volcanic eruptions? So based on the cross-cutting relationship of pyroclast deposits and nearby young impact craters, and several patches of recent pyroclast deposits were discovered, and one pyroclast deposit has a well-resolved composition using the low-orbit observation by the X-ray spectrometer on board the MESSENGER. It was discovered that compared with the surrounding terrain, the calcium content seems to be higher in the surrounding terrain, but the iron content seems to be also higher, but the sulfur content seems to be much lower. So a straightforward interpretation for this is that the material should be depleted with sulfur, and sulfur might be volatile, triggering the eruption. So there are recent pyroclast eruption on the surface. Another thing is hollows. We know that Mercury has a lot of volatiles, and on the surface we have a lot of bright haloed hollows, and those hollows are very recent.
So please try to go to the conclusions.
Okay. So we have recent volatile activity. So graphite, the content of graphite should be very low instead of weight percent of content. This is our recent study as well. We only need 0.5 weight percent of graphite to cause the global low reflectance of Mercury. Okay, so with the conclusion that we still have a lot of unknown questions about Mercury, and we're looking forward very much for the next detection of Epicolombo mission. Thank you. Sorry for the delay.
Thank you very much. So we have time for very quick question. Okay. There is no question, so we move to the next. Presentation.
Thank you.
The title of the next presentation: Design and Optimizing an Interplanetary Trajectory of a Spacecraft to Mercury. And the name of the presenter, Olga Chernenko.
Okay, so good morning, dear colleagues. I am very glad to see you all today, as well as online listeners and broadcast watchers. And today I would like to tell you about design and optimizing an interplanetary trajectory of a spacecraft to Mercury. Um, and so, first of all, we need to define why do we need to research and exploration the Mercury. And first of all, it's of course ice at the poles, because Mercury is the closest planet to the Sun, but also has some ice at poles. And of course, its magnetosphere, because Mercury's magnetosphere is closest to magnetic dipole, and it compare this planet closer to Earth in this field. And the next one, of course, exosphere. Mercury has only exosphere with various molecules, and the precision of perihelion of Mercury. So these individuals of Mercury try to understand the nature of gravity. And the next one is Mercury's inner structure, because Mercury has iron nickel core, 85% of whole mass and whole volume. And this is huge liquid iron core creates a magnetic dipole. But we will talk about astrodynamics and astrodynamics field of study of Mercury. Only two spacecraft reached Mercury, and one, BepiColombo, as you know, is flying to Mercury right now. The first one is Mariner 2. This spacecraft didn't insert into Mercury's orbit, just did 3 flybys, and these spacecraft instruments cover 46% of surface. And the next one is Messenger spacecraft. This is the reference spacecraft of this thesis. And of course, instruments of this spacecraft was more accuracy, and 4 years of operating in orbit did some investigations and opens in many areas. But the way is BepiColombo will fly 80 years before insertion into the orbit, and the Messenger flight 6.6 years to Mercury. This is only 3 years less than New Horizons flight to the Pluto, but distances is quite huge before Mercury and Pluto. And so the key idea of the work is optimization problem of flight from near Earth to near Mercurian orbit. So the first of all, requirement analysis and criteria. We need to design the trajectory no worse than existing missions. It's Messenger, 6.5 years, and BepiColombo. Now it will be 8 years flight. And as you can see, there is total delta V, characteristic velocity. Pay attention that this value is the key of optimization problem as well as time of flight. And as you can see, there is deep space maneuvers between the nodal points of the route. Deep space maneuver is maneuver when engine or spacecraft turns on. And for phasing and corrective after gravity assist maneuvers. And as you can see at Messenger, there is 5 deep space maneuvers between Mercury orbit insertion, only without between Venus. 2 Venus nodal points, and after first Earth flyby. And so, first of all, we need to consider the optimization problem argument space and the value of optimization. It will be total characteristic velocity, which is a summary of departure impulse, arrival impulse, gravity assist for saving the fuel. It will be passive. And deep space maneuvers at each nodal points of the road. It's the new one of the work for flying to Mercury. And the definition of values is Lambert equation, because Lambert equation can easier to define the conic section between two nodal points and to find the answer about initial and final velocities at each nodal points. And program argument space also is time of flight for between nodal points, planets, and the heliocentric distance of deep space maneuvers. And the numerical method is evolutional strategy with covariance matrix adaptation. Briefly, it's methods based on evolution strategy. So in these methods, we operate with mutation, selection, and recombination, but elite individuals, it's our vector of problem argument space. And at these points, at the first, it's problem argument space at many various. And then in this cloud will be more elongated to the optimal solution. Thick point at the center is expected value. So simulation reference date was the 29th of May 2040. I know further questions, why so long, but this is more how to say, this is not the optimum, because we can find more and more, because the population is random. All runs of this program simulation, and just for ephemeris of planets after 2040, it's will be maybe more optimal, but we can also find answers less than 2040 earlier. And so two roads which I founded is the first one is this is one less nodal points that in Messenger spacecraft, and in a year earlier, as you can see, first and second roads to Earth, to Venus, and in 3 Mercuries. The first US is upper stage impulse of velocity, and MOI is Mercury orbit insertion impulse to did the orbit of spacecraft closed, because we start with hyperbolic velocity. And so actual dates you can see, and Mercury approaches with time also. So this is the first road. All the first picture is ecliptic plane, so we see perpendicular to ecliptic plane, counterclockwise direction of movement. And the second one is XZ plane. It's this side, right? This side, to see the inclination of spacecraft after each movement, after gravity space, deep space maneuvers and gravity assist maneuvers. And this is the second one. So yes, you can see the inclination changes very often. So design of mission parameters, upper stage impulses you can see on the pictures, gravity assist maneuvers with the planets and their dates and current time, and Mercury orbit insertion, and the important value is total delta V, because we defined that we can fly 1 year earlier than Messenger spacecraft, but maybe total delta V is a little more, but not so much. as I guess. And so there is on the right side there is deep space maneuvers impulse values. And of course, to prove the real of maybe these further missions, there is fuel and mass estimation that was defined by Tsiolkovsky rocket equation. And as you can see, three launch vehicles, Angara, Ariane 5, and Chang'e 5, will operate with this mission with these values of orbit height, upper stage specific impulse, and the spacecraft launch mass with these launch vehicles. So, in conclusion, I wanted to say that the problem was addressed using an evolution strategy with covariance matrix adaptation. A result of strategy is several trajectories, two in our were obtained that are similar to the Messenger strategy, but has some deviations aimed to improving flying efficiency, and the deviations in the trajectories were made to enhance flight efficiency in terms of time and energy consumption. The spacecraft's mass and fuel reserves were assessed prior to its launch into low Earth orbit, and the assessment were conducted considering different launch vehicles for the spacecraft launch. So, thank you for your attention. I would like to answer all your questions.
Thank you. So, please, question. Okay, so there is no question. In this case, we move to the next talk. The title of the next talk. Mapping of polar lunar water, and this talk will be presented by Anton Sanin.
Good morning, dear colleagues. I would like to speak about our results which we obtained using land data which was accumulated during more than 13 years of neutron observation of the Moon. So I would like to start my presentation by reminding of what a number of hypotheses exist about the nature of water on the Moon. There are a lot of such hypotheses, and there are three classes of them. And first class is water was brought to the Moon by comets and asteroids. The second class is water was produced by solar wind protons which interacted with Moon regolith and produce water in subsurface. And the third class is water preserved in the interior of the Moon during from the time of lunar creation of on the orbit. So possible location of water ice on the Moon may also point of speculations. And first hypothesis water ice accumulated in permanently shadowed regions, which is very cold places on the surface of the Moon, and water ice may be preserved during a geologically long time on these places. And also there are several indications that water ice may be preserved in some depth on the regolith in sunlit polar regions. So one of the most popular methods to test presence of water ice in subsurface regolith is the neutron spectroscopy method. This method uses neutron flux escaped from the surface of the moon, and this neutrons produced by galactic cosmic rays which interact in subsurface with nuclei of regolith and produce neutrons. These neutrons traveling in subsurface lose energy and escape from surface with some lower energy. And if some amount of hydrogen present in this regolith, the spectrum of neutrons changes, and if we measure the difference between spectrum of leakage neutron, we may estimate amount of hydrogen present in a regolith. So on the right part of the slide, for comparison, I show two spectrum of neutrons. The blue line corresponds to the spectrum of neutrons escaping from very dry regolith, no water or hydrogen presence, and red line corresponds to a spectrum of regolith with 5 mass percentage of water. So in our department we create land instrument for the NASA LRO mission, and this instrument utilizes described about method of neutron spectroscopy. The instrument contains 9 neutron detectors and passive neutron collimated, which provide us narrow field of view, and we may investigate distribution of water ice with quite high spatial resolution, up to 10 kilometers from the orbit of about 50 kilometers the spacecraft is operating. So our instrument operating till now, and we continue accumulate data. And here I present most recent map which we created recently, and on this map, this is a map of south polar regions from 80 degree of latitude till pole. The poles here in the center of this map. By gray shadow we present topography here, and by black contours we present contours of permanently shadowed regions, and by different color from blue to violet we present a different amount of water ice in subsurface regolith. Our instrument sensitive to the presence of water to the depth of about 1 meter, and this is not a limitation for instrument itself. This is a limitation of physical method which I described above. So if you see on this map, you may see what a lot of water ice present inside particular permanently shadowed regions, and even around of them. So the case of Cabeus crater, Faustini, Havers and Shoemaker craters, this is the places with highest amount of hydrogen. And case of Cabeus crater, this is high most water rich area on the moon. So also from this map you may see that not all contours of permanently shadowed regions contain a lot of signature of water ice. Some contours does not contain water. But from another hand, there are a lot of bluish spots on sunlit areas, which indicate presence of water ice in regolith of sunlit areas. So the first question which one may ask, does permanently shadowed regions contain more water ice relative to vicinity of this area, which but located on same latitude belt? We analyzed our data and found that only about 5% of permanently shadowed regions contain more water when surrounding sunlit regions. Most permanently shadowed regions have the same amount of water ice. So we may compare our data with data of another instrument. Here, for example, I show comparison with M-Cube instrument data, which is using infrared observation of lunar surface, provides the signature of places where some water ice may located on the surface of the moon. So we may compare our data shown on the right part of the slide by different color, and on the left part of the slide the M-Cube data show by stars. This is a place where this instrument predict located of water ice on the surface of moon. There are quite a good correlation between location of M-Cube water ice signature with permanently shadowed regions, and also you may see that our land data show a lot of water ice inside contour of PSR, but also violet contour of land water signature propagate outside of permanently shadowed regions on sunlit area. So we may also compare land data with topography and temperature of surface, and on this slide we show cross-section along the longitude of Cabeus crater regions, and this cross-section was done from the point where L-cross experiment was performed. So on the right top figure I show land counting rate independence of longitude. On the middle left part of the slide we show topography data. This is elevation in meter, again along the longitude direction, and on the right bottom figure we present temperature of the surface, and the boundary of permanently shadowed regions are shown here by a vertical dashed line. The place where L-cross experiment was performed shown by red stars on this free picture, and we found what correlation between land counting rate and topography data, or land data and temperature are quite good and as high as 0.8. This is quite a good correlation, and one of the most interesting finding here is what L-cross experiment was performed in the point with most coldest temperature inside the permanently shadow of Cabeus crater, and this point very good correlate with our point where we estimate most amount of water signature. So our instrument does not sensitive to the layering possible layering distribution of water ice, and we may use L-cross data which found about 5.6 weight percentage of water ice in the place where experiment was performed, and if we use this data and compare to our measurement, we may estimate what about 90 centimeter of dry top layer may be exist in the place where L-cross experiment was performed. So by this comparison we may estimate thickness of possible dry layer, and it is possible that in some sunlit area with similar layering structure exists, and the dry layer on top of water-rich area, water-rich layer may preserve the water from evaporation during high temperature in the day and time of the moon. So my conclusion here is what more than 13 years of accumulated data of land on the orbit around the moon provide us a huge amount of observational data and in South Polar regions. The hypothesis that permanently shadowed regions are only reservoirs of water ice is not supported by land data, and even assumption of all permanently shadowed regions contain significant amount of water ice is not supported by land observation. Most significant amount of water ice on South Polar region of the moon was found in Cabelos, Shoemaker and Haworth crater. This is about from 0.34 to 0.52 weight percentage. In case of Cabelos PSR is the most hydrogen-rich area. Observed neutron suppression correlates with topography and temperature profiles in this place. The minimum neutron flux or signature of maximal water ice was found where temperature is lowest and consists with L-cross impact site. Land data indicate presence of water ice in regolith in sunlit area. This can be explained by layered structure of water ice deposits in regolith. For example, a deeper layer of regolith in water ice is covered by dry layer in sunlit area, and in the PSR this structure may also be covered by a thin permafrost water ice on the surface. So this is all from my side, and I am open for question.
Thank you very much. So we have some time for questions. No enthusiasm for morning session. So there is no question, but just a quick addition to the presentation. You may find additional information about the topic, about the land data and the recent publications in solar system research. So if you like, some paper already published. So okay, so we thank you again for the presenter, and we move to the next talk. The title of the talk, Lobate Rimit craters in the PSR parts of the lunar south polar craters Faustini and Shoemaker. And as far as I understand, it will be presented by Sergei Krasilnikov and the co-authors Basilevsky and Ivanov.
Yes, thank you very much. Can you hear me?
Yes.
Okay. Let's start. I'm glad to present our first and preliminary results of our project, which about the laboratory craters in permanently shadowed region of the lunar polar region. And particularly, we are studying the area of the floor of Faustini and Shoemaker crater. And it's not working? It's working. As presented in the previous presentation, the South Pole area is quite intriguing place and quite interesting because of mainly because of the high concentration of the hydrogen and the ice by itself. So that's why this area is quite popular for the future space missions like Artemis program, Chinese mission, Russian mission, and Indian. So in our project, we are our focus on the two craters. It is Shoemaker and Faustini crater with one of the highest concentration of hydrogen in this area. And thanks to the shadow camera which on board on the Korean spacecraft, and we can see the high resolution images of these permanently shadowed regions. It's allowed us to make a morphology map studying the morphology, geology, and this area, which was covered just a few years before we got this new information from the satellite. So, and as you can see, laboratory craters have a prominent rim with clear outer ends, which is not typical for the impact craters in this area and generally for the lunar craters, these sites. And it is typical for the different size. As you can see on the right image, we have about 1 kilometer diameter fresh crater, and on the left side we have about 4 kilometer diameter older crater. So doesn't matter the size or the elders. So we have the similar pattern of the morphology. And back to the literature review, we can understand that this type of morphology could be formed in the target reached by the volatiles and especially water ice. Because, for example, from the first experiment, when we fall the steel ball in the viscous plastic gel, we are expecting the similar morphology of the rims with steeper outer slopes and flatter inner slopes, which is also not typical for the just the usual impact craters. From our previous experiments and calculations with seismic shaking, we also understand that this rim formation is also quite typical for this type of the nature, the nature of when we have some volatiles in the target area. So what about our profiles? If we measure the morphology and morphometry of our craters, our starting craters in this area, we have a similar result. So with higher inclination of the slope of the outer slopes and the latter inner slope of the crater, and that gives us opportunity to make some preliminary conclusions that lobate rim craters could be found in the south pole area of the moon, and this type of craters is quite new for the moon or for the other planetary bodies. These craters have no typical morphology, and can be found in the other places. And based on the previously published results, we can assume that the target have some volatiles in the regolith, but because of lack enough impact models for these types of regoliths, we need to conduct more experimental modeling and numerical calculation with ice bearing targets and conduct some experiments in it. So thank you very much. If you have any questions, I'm glad to answer it.
Thank you. So we have time for questions, a lot of time, I would say. Okay, because there is no question, it was the last talk in the morning session before the coffee break. So now we have a coffee break, and I suggest to join in the conference room at 12 o'clock.
Увеличить или уменьшить? Сейчас посмотрим, где тут настройка звука. Сейчас звук не надо.
Dear colleagues, we are continuing our session, our moon session. In the first presentation after the coffee break, have the title Lunar Dusty Plasma and its Investigation Proposal. And this talk will be presented by Ilya Kuznetsov.
Good morning, dear colleagues. I would like to have a brief talk about some investigation proposals, and already one of them was launched mission about the investigation of the lunar dusty plasma. Basically, the dusts and dusty plasma is almost everywhere in the universe. These small particles in 1 millimeter in diameter and smaller are present everywhere in the universe, in the solar system, on Earth, on atmosphere, Lagrangian points, and of course in the lunar exosphere. These dusty particles and dusty plasma in the lunar exosphere was firstly observed on the first lunar missions by surveyors and by astronauts from Apollo missions. It was detected that the sunlight scattering on the dust particles that lifted up and presents above the lunar surface on the various heights. And also during the manned exploration by Apollo astronauts, they met a lot of big problems that connected with dust particles. For example, in this report from Geyer in 2005, it was stated that a lot of absolutely different problems that caused by dust was experienced by Apollo astronauts. For example, it's covering the lenses, it's the surfaces of solar arrays and radiators covered by dust. It's extravehicular activity suit damaging by the dust particles. After the 3 days, there were no possible to maintain the pressure in the suit when you work outside of the habitat. And also the astronauts was tasted these particles, smelled it, and it's of course it's not so healthy. They are small, they are they can be like very like knives, like maybe we can for example connect them to Japanese shurikens that can damage lungs and everything inside your body. It's important to investigate what is the dust dynamics and how we can defeat it, how can we defeat the dust activity, so it's not to damage people on the moon and the equipment on the moon. For the factors that can cause the dust activity, first one I will mention the anthropogenical activity, because after this Apollo experience and some non-manned spacecraft experience, we can see that any activity on the lunar surface, like walking or riding by car or landing by spacecraft, cause big clouds of dust, then arises, and it's charged dust. It can fall down for days or weeks and cover all by itself. And other factors that can cause the dust activity, let we call it nominal dust activity without human presence. It's bombardment of the micrometeorites, it's maybe some seismic activity, it's thermal effects on the lunar terminator regions when you have very fast changes of the temperature, and therefore the expansion of the dust particles. And of course it's a set of plasma and electromagnetic conditions. It's solar wind that influences on the lunar exosphere every time for its electrons and ions for the lunar day, it's electrons for the lunar night, and of course it's ultraviolet radiation that can cause photo effect, and photoelectrons left the surface, and therefore the dust particles and surface charges are charging. These factors causes the near surface electric fields. There are also places that contain local magnetic fields, so-called lunar magnetic swirls. And a lot of interesting effect we can observe during the passing the moon by the moon through the Earth's magnetospheric tail. So here you can see how these particles can look. These particles was the right side of them, the right photos was taken from the particles that was executed from the spacesuit of the astronauts. So mostly there are less than 50 microns in diameter, and mostly there are don't have some regular forms, and have a very strong adhesion force to every surface they met, and can go through due to their small dimensions, can go through a lot of materials and damage them. As I already told, the lunar dust activity without some mechanical forces can be caused by electromagnetic forces, in the case if they are they can dominate above the adhesion. There were some theoretical reports that calculated the necessary electromagnetical field that can cause the dust activity for different bodies, taking into account the gravitation of these bodies. However, and I will speak about this tomorrow, some experiments can show us that the necessary electric field is not so strong to cause the dust activity. It is much less than this theoretical prediction, including the big dust particles up to 50 microns and more. So for now we can tell that lunar exosphere is a very interesting, very big natural laboratory to investigate this dust activity, how the dust dynamics starts, how it works, and how we can preserve ourselves from this dust activity during the lunar exploration. Our team was developed the PML instrument, which is needed to investigate the lunar dust fluxes. The sensors of this instrument can measure momentum, charge of dust particle, and also it can measure the near surface electrostatic field and plasma with two Langmuir probes. So for the measurement we use on the upper surface, you can see the charge sensitive grid. When the dust particle falls through this grid, we can see its charge and also time when it passed. And beyond this grid there are 24 piezo ceramic sensors. Total aperture is 15 to 15 centimeters. These piezoceramic sensors are sensitive for the dust particle momentums with the sensitivity up to 10 in the power of minus 12 kilograms per meter per second, and it's it corresponds with, for example, dust particle of ferrum with 5 microns in diameter and 2 meter per second speed. And for the lunar exosphere and its not so dense plasma conditions, special Langmuir probe was developed with the range of the potential swipe from minus 88 to up to plus 88 volts, which could enlarge our detection range up to 3 to the 10 on the power of minus 12 amperes to detect the variations in the currents and so on, to detect specifically the densities of electrons and ions and so on. For the charge sensitive grid, we have a sensitivity of 10,000 electrons for the one dust particle, and mostly it should be good enough to measure any of the dust particle that was exposed to the sun ultraviolet irradiation. This instrument was already near the moon. It was located on the Lunar 25 spacecraft. It was switched on the lunar orbits and measured couple of activities, couple of events of the dust particles that hit the body of the instrument. And also it measures the plasma conditions near the on the lunar orbit. However, to our disappointment, it was after this it was not of a lot of success with this mission. So another thing that I have to told about this instrument, that now we are developing the very similar, pretty the same instrument for the Chang'e 7 Chinese mission, and it will be placed also on board the spacecraft and landed on the near the South Pole. It's like near 85 degrees, if I remember correctly. The launch is scheduled to 2026. Also, I would like to say about the next generation of this instrument that we are developing now these days. It's the instrument for the next lunar mission from Russia, Luna 27 lander. It will contain impact sensor unit, of course, with some improved schematics and measurement techniques according to our experience. It will also contain 2 Langmuir probes on the spacecraft body, and the very important difference is that we will have 2 booms on the spacecraft that will place our sensors far away from the spacecraft. It's Langmuir probes, 3 Langmuir probes on the different levels above the lunar surface, and on the at least 1 meter from the spacecraft body. And the impact sensor with charge sensitive sensor that will be placed close to lunar surface, more closer there than it would be possible to place it on the spacecraft body. So with this configuration we can eliminate the spacecraft influence on the lunar exosphere, and measure this dusty plasma more correctly, in the more correct ways. So here are the main parameters of this instrument. It basically in the construction it will not be a lot of changes. The constructions shows us it's pretty well for the cosmic mission and could survive for all the tests. However, we added some spherical Langmuir probes for the plasma detection. We add another charge-sensitive detectors, including second charge-sensitive grid. It would provide us more accurate measurements of the dust particles. And all of this will be fed with 3.5 kilograms and with power consumption less than 12 watts. Our another proposal, it's based also on the PML instrument and measurement techniques, and it is for orbits. And I want to say it's not just for the moon. Of course, we can use these techniques pretty everywhere in the solar system. if it's lunar orbit, Martian system, Venus orbit, or everywhere else. It is a very sensitive instrument with a very big range of the velocity to mass ratio, and it is quite enough to measure all of the dust fluxes. Would it be meteoroids fluxes, or maybe dust from the surface of the asteroids, comets, or moons, or anything else. And we also have a suggestion to highly enlarge our aperture with very low mass addition. So it is
2 minutes left. 2 minutes left.
Okay, thank you. Almost finished. So we suggest to use these small piezoelectric sensors to locate them on the solar arrays. If they are flat, it's brilliant. If they are, they have some perforation, that we can just have thin foil to locate these sensors, and with not a big addition of the mass, we would get the apertures as much as 1 square meter, 2 square meters, and so as much as solar panel and its dimensions. So it's some estimations what can be what can be the parameters of this instrument. So with these special separate sensors on the solar array, we can fit in the mass of the 3 kilograms, and for the measurements, it is very large range, and mostly it ends just when the energy of the dust particles is enough to damage the sensor. And all of the less particles with less speeds, we can measure very correct with this technique. So my last slides, it's the status of the instrument that Luna 25 launched, worked on orbit, but so we know. Now the PML for Chang'e 7 is manufacturing, and going to deliver to the China site this year. And PML extended version is in developing. So thank you for your attention. That's it.
Thank you. So please question.
Thanks a lot for your nice talk. I have one question. The planned lifetime of your detection, what's the, I mean, how long it will work on the orbit or when it landed? And do you care about the change during the lifetime, the change of the detection value? Okay, thank you very much. I mean, the lifetime of your detection detector.
The time of the detection of particles.
Yeah.
So for measurement, we just we have if I understood the question correctly, for measurements of the dust particles that hits the dust instrument, we have the time of passing these dust particles through the charge-sensitive grid, the time of its hitting the momentum dust detector, piezo detector, and with these 2 times we also have speed for the dust particles. So it's for these measurement techniques. And if for the procedure of measurement, so it's like non-stop every time monitoring conditions. You just switch on the instrument and it measures every time while it's enough energy on the spacecraft.
Okay, thank you.
Good morning for your presentation, and I have only one question. It's too hard to understand. What do you mean when tell flux?
By dust flux, we mean the flux of dust particles that goes through the let's say surface of the instrument. It's amount of dust particles.
Is there any way to tell apart what is the source of the dust? Like when you have in-cruise measurement, could you tell apart where the dust was originated from? Meteorites, asteroids, or from planets, or something like that?
It's very good questions. It's always the question for us. So I can tell you that it is basically it is speeds, velocities of the particles, relative velocities to the instrument. While it is located on the lunar surface, so you can tell the dust was just rise up to 1 meter and falls down, or it was a micrometeoroid. So it's a big difference in the velocities. On the, for example, lunar orbits, it's a bit complicated. However, when you have let's say the particle from Pleiades, then you also have very big speeds, velocities like 50 kilometers per second, and it is when you're on orbit, you can measure it like a relative speed as 48 to 52 kilometers per second, for example. So orbital velocity gives us plus minus 2 kilometers per second. For the orbital dust particles, you understand it's much less velocity. It's up to also 4 kilometers per second if you are on the contrary ways, or it could be even meters per second, maybe if you just catch it carefully and softly.
We need to move to the next talk. The title of the next presentation is Lunar Craters Without Signs of the Matter Melting and the Matter Emissions, and as far as I understand, it will be presented by Mikhail Shepkin.
My question is, yesterday my sound was problem. Is it okay today?
It's okay.
No, no answer.
It's okay, we can hear you. You can go on.
I can begin.
Mikhail, do you hear us?
I will talk about lunar craters without signs of the matter melting and matter emissions. Maybe it would be better say not signs but evidences. But we remain the science, it will be clear some later. It also is better. Second, my co-author is Ricardo Ferreira. It is National University of Córdoba, Argentina. He is expert in field of nonlinear dynamics. Ricardo visited Russia several times and visited Kazan and visited our conference on the North Caucasus. Conference in Terskol place several times. Some notes about Aitken crater. This is view, general view of crater in 3D mode. 3D mode from a lunar quick map. You can see some interesting elements of relief on the bottom of the crater. It is yellow it is so-called central peak of crater. It is separate peaks, mountain peaks. It is number 2 is so-called glacier-like tongue, and 4 is so-called region of bulbous fields. The thing is, Aitken crater is located in very lucky selenographic position because he is located on the edge of, directly on the edge of big crater, which is the central crater of the South Pole Aitken basin. Because the crater is located on the emission materials from basin, it is one is the most young craters because the Aspire basin, South Pole basin, we believe is the most young basin on the moon. We began our investigation in Aitken crater several years ago, maybe greater than 10 years. First, our papers and results were devoted to the coordinate system around this crater. Moreover, the Aitken crater became the first crater where we tried to compare the height of lunar elements obtained by laser orbital laser altimeter and by photogrammetric technique. Then we turned to creation of spatial models of different and separate elements of this crater. For example, we obtained the high resolution 3D model of so-called glacier-like tongue. You can see this image, this tongue. big mountains back front. It is central peak of Aitken crater in large scale. You can see here separate bolts in front of separate boulders in front of town. Our last result concern the three model of so-called bulbous fields in the crater. I mean this region, number 4. There are 5 small craters, 1, 2, 3, 4, and 5. And last year we presented special report at symposium of solar system. The paper is published in book of abstract. And main result of our last investigation were the digital model. That is model of high resolution obtained on the basis of Apollo and Zond images, orbital images, made by means of metric cameras. You can see here all 5 craters, 1, 2, 3, 4, and 5 in digital mode. But you can turn your attention to one of them. It is here. When we obtain the result, we cannot understand why he is so deep, in spite of diameters of craters almost the same. And motivation our next study were to find on the moon the craters which are similar to this one. You can see the list of craters which we found especially for this goal. First, in this table, we located 6 craters. The bottom of which is very unusual. And first of them, it is crater in Aitken crater near the crater J. J it is an official name. These craters are nameless, but 2 of them, Chebyshev B and Sanford C, have your own names. There are long and latitude and longitude position of craters. D1, it is rim, diameter of rim crater. D2, diameter of floor crater. I'd like to show you only 2 positions from this list. I mean Chebyshev B and Sanford C. Chebyshev B left side below, Sanford C right side below. It is so-called section and height profile obtained our by means of lunar peak map. You can see here that the surface of bottom of floor of crater is unusual in sense of there are no signs of melting, and we can see another surface. It is hard to believe, but this surface is very similar to solid surface of some kind solid impactor, which is located in the subsurface lava field. I'd like to turn your attention in shape of flow profile. There are no central peak in usual sense. This and this one. It is an unusual flow from point of view classical imagination about impact craters. And we are going to turn attention of planetologists and geologists on these craters, because maybe these craters may consist from part of a meteorite or asteroid which are not destroyed in moment of falling on the moon. Three last positions in this table belong to the Mare Orientale. It is also a young region on the moon, but I want to say that this data include into table, but requires more detail. Consider, because it only recently was found. The main result of our studies consists of the such kind of bottom of floor of crater. Maybe consist of from part of small asteroids and meteorites, which are not destroyed in moment of falling from the moon. We believe that such craters may be objects of increased interest for upcoming lunar expedition. Thank you very much.
Thank you. So please questions. Lev Matveevich.
Sorry, sound was not so good. Maybe I missed this point. My question is there any limitation on the velocity of impactor to have such type of crater you described without melting? Should be low velocity impactor. Should be. Is there any some limit?
Indeed, the velocity must be small. It's surprised me because usually we see the asteroids and meteorite with big speeds, but it is a mysterious situation. You can see all these craters directly on the lunar quick map on the basis of this table. It's a very easy to look to see this craters his bottom.
Okay, we need to move to the next next talk. It will be the last talk before the lunch. So the title of the talk: Global Hall MHD simulation of solar wind implantation flux on the lunar surface, and an excuse again for the not correct pronounce of the family name. It will be presented by Lian Xi and Lei Li. So please proceed.
Okay. Thank you. Thanks for the introduction. Can you hear me?
Yes.
Okay, I will share my screen first. And okay, can you see my presentation?
Yes, it's okay.
Okay, thank you. Hello everyone, I'm Liang Haixie from National Space Center, Chinese Academy of Sciences. And the title of my presentation is the Global Hall MHD Simulations of the Solar Wind Implantation Flux on the Lunar Surface. First, I'd like to give a brief introduction about the background. We know the Moon represents an airless body with no global magnetic field, no dense atmosphere. So the solar wind can directly interact with the lunar surface, with most of them absorbed on the day side, leaving a plasma void on the night side. And such an interaction can change the physical and chemical properties of the lunar soil. And we call this process the space weathering effect. Meanwhile, some component of the lunar soil can be released from the surface, such as the oxygen, silicon, and iron, which can provide an important source for the lunar exosphere. Recent observations have shown that the solar wind implantation can bring some water molecules on the lunar surface, and we can find a diurnal variation of the water abundance of the lunar surface, where we can see that the water abundance near the terminate can be higher than the subsolar region. And we also can find that the water abundance can increase with the latitude caused by the lower temperature near the polar region. And one of the interesting things is that people find a south-north asymmetry in the water abundance, where the water in the northern hemisphere is generally higher than that in the southern hemisphere. The reason is still unclear. And on the other hand, although the Moon does not have a global magnetic field, it has some local cross field called the magnetic anomalies. And the strongest magnetic anomalies is located on the lunar far side in the southern hemisphere. And the observations have shown that these strong cross magnetic field can stop the solar wind and reduce the solar wind flux on the lunar surface. And we call it a lunar mini magnetosphere, which is similar to the Earth's magnetosphere, but with a smaller size. And due to the magnetic shielding of the mini magnetosphere, we can find that the space weathering process can be reduced in this region, and we can find a lunar swirl, as shown in this figure. the lunar surface can be less space weathered and with a brighter patterns. And also, people have found that in this region, the water abundance can be relatively lower than the surrounding region, which suggests that the magnetic anomalies can reduce the space weathering and the water generation processes on the lunar surface. So it is important to know the solar wind implantation flux for both the space weathering and the water generation studies on the lunar surface. And specifically, we need to know how much solar wind fluxes can be reduced by magnetic anomalies. Here we present a global 4-MHD model to simulate the solar wind interaction with the lunar magnetic anomalies. We use a 415 degrees spherical harmonic model for the cross field and a locally refined spherical grid in the SSE coordinate, in which the x-axis is pointing to the sun, and the z-axis is perpendicular to the ecliptic plane. And the smallest grid near the surface is 8 kilometers, which is small enough to reproduce the fan structure of the crust field. Here the simulation result. As shown in the left figure, we can see the simulation can produce a mini magnetosphere caused by the cross field on the lunar far side. And we compare the simulation result with the observations from the Artemis spacecraft. As shown on the right figure, we can see in this figure the solid lines represent the observations from Artemis spacecraft, and the dashed line is obtained from the simulation. We can see both the simulation and the observations show similar shock structure around 2 and 15 o'clock, and including the jumps in the density and the magnetic field strength, and deceleration and deflection of the velocity and rotations in the magnetic field. And meanwhile, the simulation can reproduce the reduced solar wind flux on the lunar surface, which is consistent with the Chang'e 4 observation on the lunar surface. As shown in this figure, it is found that the solar wind flux can be reduced a half on the surface, and such a value is also reproduced by the simulation. Sorry. As a result, we think our model is valid for the simulation between the solar wind interaction between the solar wind and the cross field, and can be used to study the solar wind implantation flux on the lunar surface. Sorry, this should be a cartoon. Yeah. In reality, the moon can move around the Earth and spend about 1/4 of its time in the Earth's magnetosphere. So we also study the solar wind implantation flux when the moon at the different locations during the orbit around the moon, around the Earth. And the simulation result are shown on the right figure. You can see the solar wind implant flux is maximum at the subsolar point, and decrease with the solar zenith angle. In addition, we can find that when the moon is in the Earth's magnetosphere, the flux can be bulkily reduced, as shown, and when the subsolar point is close to the 0 degrees longitude. And in addition, we can find that there are some local cavities in the map, which is caused by the shielding of the local cross field. To investigate the long-term effect of the solar wind implantation flux to the and evaluate effects on the space weathering and the water generation processes on the lunar surface, we calculated the average implantation flux over a month. And the left figure shows the cross field on the lunar surface, and the number flux, the average number flux, and the energy flux, respectively. And it is interesting to find that we can reproduce the all the lunar swirls that have been founded so far, which is listed in this table, and also marked by the squares in this figure. And we can see that all the local cavities are co-located with the swirls listed in this table. And other observations have shown that some swirls with no water content, as shown this figure. So we think our model can reproduce the can successfully capture the magnetic shielding effects caused by the lunar magnetic anomalies. As we can see that the lunar magnetic anomalies are more likely located on in the southern hemisphere, and we can expect a south-north asymmetry in the implantation flux. Here we calculated the implantation flux in different latitude range. We divided into 3 ranges known as the low latitude and the middle latitude and high latitude ranges, respectively. And we can see that the implantation flux in the southern hemisphere is can be generally lower than those in the northern hemisphere, especially for the low and middle latitude ranges. And the maximum difference can be as large as 15%. According to the previous observation, that the lunar that the water abundance in the southern hemisphere is lower than that in the northern hemisphere, and the Monte Carlo simulation have shown that the water molecules caused by the solar wind implantation can be migrate from the subsolar and region to the polar region. So we suggest that the such a south-north asymmetry in the water abundance can be caused by the magnetic shielding of the cross field, as shown in our simulation. Here we come to the summary. First, we provide a global map of the solar wind implantation flux. And we find some local cavities in the flux map, which are connected communicated with the lunar walls. And we also find a south-north asymmetry in the flux map, and which can be used to explain the neural water content observed in the southern hemisphere. And next, we can use the obtained implantation flux to study the related space weathering and water generation processes. Here I showed our preliminary studies on the multicolor simulation of the migration of water molecules caused by the solar wind implantation. And we have considered the shading effects of the magnetic anomalies. That's all. Thank you.
Okay, thank you very much for your presentation. So we are open for questions. Lev Matveevich.
Thank you for very important and interesting talk, but the question is, what is the estimated depth of this implantation, water implantation in lunar regolith?
Sorry? One addition.
I asking about the depth of this implantation layer, thickness.
Foundation layer. You mean this simulation step, or what else?
The question is the following: can you estimate how deep your implantation process may take? So then you speak about the hydrogen distribution or water distribution, how deep it could penetrate. It only on the surface, or it can penetrate to some deeper layers?
Okay. Actually, I'm not quite familiar with this point. As far as I know, that the observation based on the M3 data is only reflect the water abundance with a depth of less than 1 micrometers. Yes. It's all depends on the frequencies of the waves used. For the M3 data, it's located in the IR wavelengths, so it can only reflect the water abundance with a depth of several hundred nanometers. It should be is something like that.
Okay, thank you. So we need to finish our morning session. Now we have a break for a lunch. And I suggest to meet here in the conference room and to start our after lunch presentation at 2 p.m. So see you in the 1 hour.
Yes. Thank you.
Alexander. Александр, я хотел вопрос Ломакину задать. меня вопрос к модератору Александру Ломакину.
Михаил, yes.
I'm sorry, вы могли бы пригласить Ломакина к микрофону, а?
That's me, that's Lomakin. Михаил?
Да, Александр,
Да, это я.
я так и не понял, мой звук хорошо проходил или плохо?
Ну, у вас, как бы, в наушниках вас нормально слышно, а на весь зал из динамиков, ну, так.
Ага.
На...
То есть, как бы, невнятные слова или что, или уровень, шум там, что именно?
Ну, просто эхо получается.
Эхо получается?
Да.
И оно все глушит, да?
Ну, гулка просто немножко получается.
Ну, слова можно разобрать?
Нет, разобрать-то в целом можно. Все в целом нормально.
Я никак не могу понять причину.
Ну, сложно сказать. Наверное, это комбинация микрофона. Можно в целом почетче говорить.
Угу. У меня встроенный микрофон, майкрософтовский, совместный с камерой такой. Раньше, вот я когда говорю через него по Яндекс конференции, там никаких проблем нет. Как только в Zoom перехожу, так начинается.
Ну, вот я вас сейчас в наушниках еще параллельно слушаю, и из динамиков слушаю, и из наушников просто своих. В наушниках вас получше слышно, в динамиках похуже.
Угу. А вы еще будете на конференции?
Да.
И я просто хотел вас попросить, я бы просто свой динамик выключил и подключился с наушниками. Может быть, лучше стало бы попробовать все.
Вот сейчас можете попробовать, как раз можем
Ну,
поэкспериментировать.
у меня просто при себе их сейчас нет, наушников. Я, может быть, следующий перерыв или... Это все сегодня последний день, по-моему, с докладами, да?
Сейчас я посмотрю, когда вы еще... А у вас же больше нету вроде докладов?
Ну, у моего доклада прошлого нет, просто на будущее я имею в виду.
На будущее.
Да.
Ну, можете в следующий день в обед подключиться.
Там, по-моему, следующий день-то уже больше нету, а?
Нет, еще вот пятница у нас будет.
Вот я программу открыл. Нет, завтра еще есть, да.
Еще раз?
Завтра еще будет целый день. Вы завтра будете, да?
Так, можете еще раз повторить?
Завтра еще будет заседание, где я мог попробовать бы. Вы сами-то будете, потому что я там больше никого не знаю, с кем связаться.
Ну, короче, в любом случае, завтра можно кого-нибудь будет подключать, будет нормально.
Ну, хорошо, попробую завтра. Вам спасибо за помощь.
Уважаемые коллеги, у нас наступает послеобеденная сессия. Мне было велено говорить по-английски, но я немножко потренируюсь по-русски, потом на английский перейду. Я хочу сделать два объявления. Во-первых, у нас нету Ивана Агапкина презентации. Пожалуйста, загрузите, потому что у нас есть только вот одно место, где надо еще вашу презентацию загрузить. Это первое. Второе, ну, у нас достаточно заполненный день сегодня будет после обеда. Вы видите, что у нас постеры заканчиваются в 19:45, поэтому, пожалуйста, также просьба ко всем презентеры постеров, которые по какой-то причине не смогут сделать свою презентацию, пожалуйста, сообщите Анастасии, чтобы мы уже знали, что вашей презентации не будет, и чтобы мы пораньше могли закончить наше сегодняшнее заседание. И третье сообщение, значит, по практическим причинам нам пришлось в программе, вот которая сейчас начнется, переставить доклады Артема Лысенко и Майи Дичковой. Значит, Майя будет выступать в то время, которое запланировано для Лысенко. Это в 15 часов. И, соответственно, Лысенко будет выступать в 16:40. Значит, у нас произойдет смена темы и смена ведущих. В 17 часов Михаил Герасимов будет председателем. Ну и после этого, когда будут постеры, опять мне придется здесь пробовать обеспечивать порядок. So, dear colleagues, we are starting our afternoon session. I just make a short comment that we changed in the program. Talk by Maya Dichkova will be in the place of talk by Artem Lysenko, and vice versa. We will have busy afternoon today, and the chairperson will be changed in 5 p.m. Mikhail Gerasimov will make the order for the discussion of lunar samples, and we will start our poster session at 7 p.m. and I'm asking very kindly to inform us if somebody will not make his presentation or her presentation in this late evening. It will permit us to finish earlier, to give you opportunity to return home a little bit early, because we have very busy evening also. So I am starting the program. It is my pleasure to invite academician Lev Zelenyy to make a talk about polar investigations of the moon at both South Pole and North Pole. Lev, please. We decided to update you on some new ideas we have in the development of Russian program of lunar investigation and exploration. Actually, you see the title, and I illustrate the idea that we suggest to extend our studies not only the South Pole is very popular now, but also to the North Pole. And funny enough, I noticed two symbols. At the left side is Russian Academy, which is fully supportive of this idea, and another at the right corner is the Roscosmos, which is still hesitating to support and provide money. So I think we could use this meeting and this discussion as maybe arguments of our scientific community to support this idea, to show that it's scientifically very valuable and sound. I come back to this selenography, which started in 20th century. You see the symbols of landing of Soviet lunars, among them Luna 24, Luna 16, Luna 20, which delivered lunar regolith, and famous American Apollos. You see all these missions at this time have been concentrated mostly at the vicinity of equatorial region and middle latitude, because nobody realized at this time that polar regions are quite different. It's completely could be completely new plasma and environmental conditions there. And it's just easy ballistically to study this region. But 20th century changes paradigm. Many ideas emerged to study the lunar South Pole. This is American Artemis program, which I think everybody have heard about it, but is fully concentrated the lunar South Pole as a target site. Even our lunar research station joined with between China and Russia. Also, we plan to concentrate our efforts at the South Pole. And you see our we call it diagonal of our missions. Unfortunately, Luna 25 launched last year. Launch was not successful. Mission crashed, but we learned our lessons, and hopefully next our lander Luna 27 and lunar sample return missions will be successful. We plan to take into account all technical shortcomings of the previous launch. But Luna 27 itself is quite developed spacecraft. We study it at our previous we discussed it at our previous symposium last year or a year before, so I will not concentrate on it. I remember that is a spacecraft devoted to the long-term measurements of the properties of lunar regolith, contact investigation, study of lunar exosphere, lunar dust. In the morning we have heard the talk about the instruments for lunar dust studies. We already selected landing sites for Luna 27 at the South Pole, but the situation is changing all the time, and recently was published very interesting publication by Thomas Zurbuchen. Thomas Zurbuchen was former, I just happened, I know him because he worked in Switzerland where I have been, but he was the head of NASA Science for 6 years. And he says very important words that lunar marathon began. It's marathon, it's long-term studies. It's not just attempts to raise flag at the moon, as have been in 70s last year, but is already exploration. And very important words, second paragraph, the lunar South Pole could answer profound questions about the history of our solar system, processes that shaped the early Earth and extent, and study distribution of volatiles. But these spots at South Pole are few and very potentially, as I study, very potential rewarding. Actually, this announced a real competition for the resources of the South Pole region, and the humanity, the United Nations should introduce some rules of the game for this. But really, South Poles lunar poles are very important. I just want to remind you the reason for this is both Southern Pole and Northern Pole. This is related with the almost orthogonal inclination of lunar polar axis to the equatorial plane. I remind that the Earth rotation axis is inclined to much larger angle, almost 23 degrees, and it's explain our seasons. But moon is different, and this small inclination explains two remarkable features at the lunar polar region. The permanently shadowed regions, which is inside the crater, because sun direction of propagation of sunlight is almost tangential to the lunar surface. But also exist almost permanently illuminated regions. So we could have both condition, and in permanently shadowed regions, the general belief is that it may be the place of accumulation of the volatiles, and permanently illuminated region are excellent place for creation of lunar bases, because there was no limits of solar illumination during the nights. So, but the number of such places, due to specified lunar topography, is really limited, and the winner who will be first could use first all preferences of them and begin the construction of permanent settlements. Lunar poles have very interesting and complicated geology. I'm not geologist. I will not talk about this because there are many rare metals, many real remarkable resources which actually justify this period of exploration which begins now. People thinking about moon not as a site of only science, but also the next step is commercial utilization of its resources, use of moon as a starting point for the flight of Mars. So in this century we will see really the burst of the interest to the moon, and I think the second half of our century we will see those who will survive to this time, the real use of the moon as a seventh continent of the Earth. But what are the main resources at the moon? And what general belief was that the water is mainly concentrated at near the South Pole. Just before the lunch, those who have been have heard very interesting talk of our Chinese colleagues who explained the production of water due to interaction with the solar wind and explained some asymmetry, possible asymmetry of its distribution due to magnetic anomalies in the southern hemisphere. But anyway, the reason is not clear, but the moon, the water is existing at both poles of the moon, but the sides of the on the surface presence of the water ice at the South Pole are more pronounced. But they still exist also at the northern pole, and at this figure you see very important plot. Gray color shows the relief of the surface based on the data of American instrument LOLA on satellite LRO. Green color is relative content of the water ice in the lunar regolith, is the data of the Russian instrument land, and PI is our chairman, Dr. Mitrofanov. And red regions and red arrows show the possible sites of the landings of missions to the lunar poles. You see, there is quite many options to have and find very interesting places, not only at the South Pole at the right, but also at the North Pole. The number of these regions is small, it's true, but each of them is each particular of them is still contain a rather good quantity of proportion of water, and topographically is has a favorite condition, so we could choose between them. And this I don't know English word in French, azertage around the South Pole, which probably was also introduced by our measurements at LRO, is not fully justified. And our idea is to have symmetric study, to build two identical missions which could answer many important questions. And if we will be able to extend this study to both South Pole and North Pole, science return of this mission will be very significant. It doubles or maybe triples, while the cost of it is not much larger. It's, engineers estimate only 50% of additional budget you need to have two identical, if they are really identical, two identical missions. Samples of lunar regolith will be studied both at the south and north, at the depth about 1 meter. We have in Luna 27 the instruments for this, and we could estimate the composition and content of the water in these particular areas. We studied the properties of lunar dusty plasma at south and north pole, and compare the radiative processes which exist in polar regions of the moons at both sides. Of course, we know it from the Earth. There are similarity between Arctic and Antarctic, but these two continents and two regions are very different. So it's not synonyms to polar regions. Also at the moon, and there could be many interesting differences between them, which we could cover fully in our dual analysis. And what also important, that we finally arranged the global network which could be made for study lunar seismic events, because as I have told before, majority of the missions which are planned for this decade, beginning of next decade, American, Chinese, Indian, everybody is concentrating on the South Pole, and North Pole remains unattended. And of course, for astronomers will be interesting possibility to study the proper motion of the moon if we have measurements at near both poles. And we could extend our service for communication and navigation using two stations at the pole. So moon will begin to be explored already in more global and more general and more interesting context. So this is our point, and we could discuss it, scientific significance of it during this discussion. The dual Luna 27 mission with two identical, I emphasize identical because it doesn't increase cost very much, is capable to solve some outstanding scientific problem. It's cost effective, reduce non-justified distortion of science attention to both lunar hemisphere. Exploration perspective at north seems to be also very reasonable, very good. So it's our point, and I think it will be very good if Russia and which will be joined by other countries, have also its outpost not only in southern hemisphere of the moon but also at the north. Thanks for your attention.
Lev Matveevich, thank you very much for your presentation. I know from Dr. Agapkin that he will be late, unfortunately, so I suggest we may have some extra time for questions and for discussions on the topic which Lev Matveevich presented to us. So please, your questions, your opinions, because this idea of two twins at both poles is very new and important for us, and we need to have support from science, from the scientific community. So please, we have time for questions and discussion on this subject. Please, who will be first? Raise your hand. Yes, please. Mike. Somebody have to give you mic. Just a moment. Никита. Никит, отнеси, пожалуйста, микрофон. Спасибо.
Hello, Natalia Bezaeva, Vernadsky Institute. My question is, I'm very impressed by the idea to have two identical missions, and at this point it looks fully justified. But what if we still have a budget cut? Which pole you will prioritize?
This is a good question. Of course, from science point of view, it's natural. Two missions better than one, and anyway it produce interesting results. But it's not easy to justify it, and in Russia our space agency listens sometimes, but we believe and respect the opinion of scientific community. So we brought this point. It should not be some domestic decision. It should be interest of scientific community, because we believe that on important decision in space policy develops bottom up, scientific community express interest, justify this, and then agency people which should believe and follow the ideas of scientists follow it. So we bring this point as a point of discussions here, and ask for your support, and maybe people have more stereoscopic view and explain also. I don't speak about geology, I don't speak about many things here, but maybe you people who are busy with lunar geology explain why it's so important to compare lunar geology at south and north. My point was that people looking for water is there and there. So if you want exploration, rare metals in there and there, not much difference, but maybe some additional value is in comparison other features. For example, exosphere might be different. And today, I don't know if you have heard that there was very interesting talk of our Chinese colleagues before the break. They emphasize that there is real asymmetry of the moon because of presence of magnetic anomalies at the south. Maybe the other reason, maybe interaction of with solar wind should not be symmetric. It's interesting science question as well.
Thank you.
Thank you. Please, another question. Maybe if you are thinking about that. Okay.
Thank you for interesting talk. I just wanted to know what place is considered for landing site in the North Pole? Some crater or what?
It's a good question. We both at South Pole and North Pole, we should follow the technical criteria because landing station should survive. It should be sufficient illumination from the sun. It should not be dark, permanently dark region, because spacecraft will not survive. Our engineers don't know how to survive in PCR. It should be good illumination. It should be a good amount of water ice based on distant measurements, and it should be good, rather simple topography without large changes in relief. It should be rather flat. This is also should be visibility to the Earth. And if you multiply all these parameters, you get these regions I have shown by the red contours. Disappear at this map, which are good from all these four criteria are simplified. It's the same for south and poles. We don't have any special consideration to some geological features in this region. Maybe it could be done as well, but anyway, the landing site should be sufficiently flat. Is a condition of engineers who design the landing spacecraft.
If possible, I may make some short addition to this answer. You know, we are now in the 21st century when we have not the rise for the first step on the moon, but when we started our exploration of the moon. So we believe that humans come now to the moon forever, for all time. And in this sense, we consider these two landing options at South and North Pole as the creation of some settlements, of some lunar bases. And we are selecting regions not only for one particular landing, but for the future development, creation of infrastructure, and opportunities to create in future human bases. So on this map, people with a good opportunity to see may recognize red regions in the left map of south, of north, and in the right map of south, which was selected in our institute with the necessary conditions, not for the current landing, but for future exploration. And we believe that both poles has to be landed and has to be started for exploration. the most simple argument comes from astronomy. Using the two bases at two poles, we will be able to do full sky coverage. So we will be able to test for the hazard from asteroids continuously without clouds, and to give the first information about something dangerous for us. Also, people who are working for outbursts on the stellar objects will be very happy to have the constant monitoring of sky and be able to work together with the satellites to monitor the region. So we think that two poles in any case will be used by humans in future. And what we are saying, let us start with Luna 27. Luna 27 also will have additional opportunity for successful result of the landing. We remember that Soviet Union made first successful landing with Luna number 9. So we are thinking about additional redundancy of the mission to be able to provide the technology for future landings. So there are both practical needs and scientific researches.
Thank you. I just also add a couple of words. I understand the question of Dr. Demidov. It's important. We really plan to land on the criteria of flatness and non-geological criteria, but of course it will be some place where if we develop later this station in the vicinity of this region of first landing, then at further next missions we have already mobility, and you know that Dr. Slutain, your institute, is developing the rover geologist, and of course we will be able to explore some interesting geological region outside in maybe 40-50 kilometers outside this initial landing site. So we will not forget about interesting geological regions.
Maybe somebody outside of the room who participate in our session would like to make some comment or to ask some question. We listen you.
Thank you.
Oh, okay, no, there are still questions here, please.
Наше мнение разработчиков мобильной робототехники.
I would like to say that from the engineering, I'd like to say that from engineering standpoint, the approach to have two rovers or two landers on the both poles is very is good, and it's right approach, because in this case we have more mature machinery, and we will get more time to debug and develop much better device, because our always what we have in engineering, it's a low quantity of machines that we do, and their reliability is lacking the performance. But since we have two identical stations or landers, including robots, this will give them more opportunity to provide better work. That's was just a comment from engineering standpoint.
Thank you. So, as I see, there is no argument or any statement against second pole landing. So, do we have in the room somebody who have a negative view on this idea to make a north landing together with south?
These people not here, they're at 7th floor doing astronomy because it costs additional money.
Okay, people, do you listen us? So I may declare that at least in this session, in this conference, there are nobody, and we will report this result to our space agency. Thank you very much. Yep, thank you very much. So I would like to announce the next presentation. Mikhail Malenkov together with colleagues about mobile platforms, which just was mentioned when we discussed these two ladies. Please, you will have about 20 minutes.
Colleague who also head of the design department of the Scientific and Technological Center RACAT will help me to present this report. Alexei.
That's me.
Мы предполагаем показать видео на базе наших разработок, поэтому я буду
video a little bit later, so
буду очень побыстрее постараюсь показать все слайды,
and try to get faster to the end of the
чтобы успеть показать видео. Да. Да. Хорошо, спасибо. Спасибо. Ну,
окей.
Да.
Thanks.
Мой доклад развивает тему, которую мы начали на предыдущей, вернее, в 22 году на 13-м симпозиуме.
My paper presents the future continuation of previously reported paper on previous symposium on the mobile platform for lunar exploration.
Если тогда мы говорили о концепции и показывали схемы, то сегодня наша работа подошла уже к определению проектного облика машин, которые потребуются для лунной станции.
At that time we presented the concepts, the general approaches to the topic, and now we are close to engineering solutions and we are going to present them now.
Ну вот пару слайдов из прошлой презентации. Мы определились с геометрией самоходного шасси, которое может стать основой для создания луноходов различного назначения.
A couple of slides from the previous presentation where we sized the dimension and basic parameters of the mobile platform for the needs of lunar base.
Мы отталкиваемся от будущего носителя, который будет использован для создания лунной станции. Его диаметр головного обтекателя будет не меньше 5 метров.
We're starting from the size which are given by the flare of the launcher, which is about 5 meters in diameter, and that is our starting point in dimensioning.
Ну вот получилась такая геометрия. Затем выяснили, какое же может быть колесо на этом грунте, по целине этого грунта. Мы знаем его несущую способность.
So we found the overall dimensions of the payload, and we know what is the carrying capacity of the lunar soil. So we come to the definition of the wheel diameter, which is most important in the mobility.
И мы знаем, что несущую способность лунного грунта можно хорошо и просто довольно-таки увеличить простым уплотнением материала.
And we know that we can compact the lunar soil to much harder substance by just compressing it in a simple just squeezing or just hammering way.
Отталкиваясь еще от разработок группы Бармина и учитывая вот современные лунные модули Международной космической станции, мы берем такие цифры. Масса лунного модуля лунной станции примерно 18 тонн и габариты, диаметр 4 метра, длина 8 метров.
Based on the previous work led by Barmin, academician Barmin, we come to those based figures. The mass of the payload is 18 ton, and dimension. Размеры повторите.
Диаметр 4 метра, длина 8 метров.
Length of the payload, the cylinder.
Масса 18 тонн.
8 meters and diameter 4 meters.
Это позволяет нам определить необходимую мощность, но в данном случае это 340 ватт, мощность электродвигателя каждого мотор-колеса.
Knowing this, we come to the power we need to exert by the driving wheel, so it's about 340 watts per wheel. And then we come to the solving the transport task.
Ну, а затем рассмотрим вот проектный облик получающихся машин.
And now let's get into detail with the layout of the machines.
Здесь получается как минимум два варианта. Вот рассматриваем тяжелый вариант для перевозки лунных модулей.
So we come to two options of the mobile robots. It's a heavier and lighter one. And first one is heavier for transporting the lunar modules.
Это самоходное шасси.
This is a self-propelled chassis.
Это схема сложная достаточно приводов, которая у нас уже отработана и является нашим научно-техническим заделом.
And it's equipped with a rather complicated design of the so-called active suspension with few drives, but it still have our proven background and know-how.
Основой, вот мы считаем, должна быть интеллектуальная мобильная платформа на базе, значит, таких самоходных шасси, которая совершенствует, является дальнейшим развитием самоходного шасси.
So the future development of the self-propelled chassis will be so-called smart mobile platform, or intelligence mobile platform, and that will be the development and future progress of this robotics.
Это то, ничего подобного на существующих луноходах, включая и советский луноход 1-2, не было.
That was not yet has been achieved by previous roving systems, roving platforms like Soviet Lunokhod or other robots.
Это система автоматической стыковки двух и более машин.
What we did is a so-called automatic self-joining device or mechanism to form the trains of the mobile platforms from 2 to 3 and even more.
Она содержит пассивный механизм и активный механизм.
It has passive part and active part. It's numbered number 5 and number 9 on the diagram.
Снабжена камерами и блоком управления для локальной навигации, позволяющим двум и более машинам найти друг друга и произвести стыковку.
This intelligent mobile platform is equipped with a bunch of sensors in order to find themselves before docking and to realize the successful docking afterwards.
Нужно сказать, что и по этой части был создан задел еще в прошлом веке.
And it needs to be mentioned that the background for this solutions have been developed, matured, and prototyped in previous century while preparing Soviet piloted mission to the moon.
Вот такой макет был создан во ВНИИ Трансмаш еще в 1983 году, и такая была разработана схема сцепки, которая обеспечивала все требования к ней.
This prototype test mock-up has been developed in VNI Transmission and former Leningrad with the help of a specially designed hinge mechanism. It's two parts of the train have been jointed and provided good mobility for both.
Вот так выглядит сцепка из двух интеллектуальных мобильных платформ, которая позволяет перевозить модули. Вот здесь соотношение, так скажу, значит, здесь модуль 4 метра, а диаметр колеса чуть более метра.
So that's how we envisage the joining of two intelligent mobile platforms, and in order to carry the lunar module, and you see that the diameter 4 meter corresponds that our wheel is approximately 1 meter in diameter.
Ограничения следующие: угол подъема не более 12 градусов.
The restrictions are for the mobility is the slope angle is no more than 12 degrees.
Ну вот, в частности, в районе массива Малаперт есть пологие склоны, где практически выдерживаются вот такие вот углы подъема.
In particular, if we look into Mount Malapert region, there are places which answer or corresponds to this requirement of slope under 12 degrees.
Следующий легкий вариант.
And next, light version of the intelligent mobile platform.
Самоходное шасси оснащено уже другими колесами, более упругими, позволяющими двигаться с большими скоростями и уже по целине.
This platform is equipped with smaller wheels and more flexible in order to increase the rowing speed, and it has ability to move over the virgin soil.
Вот, мобильные платформы на базе этого шасси, она будет такая же, как предыдущие, вот с новыми элементами системы автоматической стыковки и управлением для того, чтобы обеспечить нормальную работу.
Similar to the version, this light platform also will be equipped with automatic docking system and ability to move autonomously in environment.
Что можно сделать на базе вот этой интеллектуальной мобильной платформы? Ну, в первую очередь, конечно, понятно, что должен быть какой-то пилотируемый луноход. Вот это проработка мобильной герметичной кабины.
What we can do in order to provide payload for this light version of the intellectual mobile platform is to equip it with a habitat, with living cabin or carriage where the cosmonauts or humans can survive the lunar environment.
Ну, основные характеристики. Общая масса 3 тонны, масса вот самоходного шасси вместе с интеллектуальными элементами 500 килограмм.
So this mass of the platform 500 kilograms, it carries the living module with mass of 3 tons.
На базе этой же интеллектуальной мобильной платформы можно сделать и следующее звено многозвенных робототехнических систем, ну или самостоятельный, но самостоятельным луноходом он не может быть. Нет, еще одно звено мобильной робототехнической системы.
We can add another block into the chain of this mobile jointed train and have
Назначение это жилой, спальный модуль и для работы космонавтов.
For instance, one of them can be just for sleeping and some for just living conditions, and another carriage can be used for working and some research activity.
Ну и еще одно звено поезда на базе буровой установки, идею которой предложила в свое время лаборатория робототехники для планетных исследований, ну, в частности, Олег Евгеньевич Козлов.
Another piece of chain for this robotic train is the drilling installation, the drilling rig. And this is based on the advice or some previous activity led by Oleg Kozlov laboratory.
Для того, чтобы полностью... Есть 5? Меньше?
4.
Тогда давайте последняя картинка. Вот это на стоянке весь лунный поезд, ну или на современном языке это многозвенная робототехническая система. Вот это в движении. И давайте посмотрим.
Robotic train in a station. And
фильм. Фильм? Давайте.
Он со звуком?
Со звуком. Шасси тяжелый вариант.
This is the design of self-propelled chassis of heavier option. Sorry, light option. This is a double wheel, flexible metal tire. All wheels are steerable, so they can afford moving in a crab-like version or spot turning in place. And the active suspension allows vehicle to adjust its clearance or provide some horizontation over the surface if needed.
Появляется оборудование, доводящее до уровня интеллектуальной мобильной платформы.
This additional avionics, the self-propelled chassis becomes an intelligent mobile platform that can move autonomously on its own.
Это единственная совершенно новая система. Сейчас она у нас находится в стадии патентования, поэтому мы не все покажем.
Quite innovative design, so it still is under patent procedure, so that's why we cannot show much.
Все звенья мобильного робототехнического комплекса будут доставляться так же, как доставлялся Луноход-1, Луноход-2 и другие.
All components of the mobile platform can be delivered to the surface of Moon same way as it was done during Russian Soviet Lunokhod time. So all the technology is available.
Вот второе звено появилось. Также доставили на Луну.
Second comes second carriage, and they can dock together to form a train, and in this case the capability of these two robots are not double. It has more coefficient of efficiency since they are connected.
С помощью камер локальной навигации достигается возможность их стыковки и производится.
Thanks for the cameras and sensors, the docking comes automatically, and the robots now
Точно так же может состыковаться и второй, и третий, и четвертый, и далее звенья.
same way, depending on the task, we can add more and more modules.
Ну и это вот положение на стоянке, когда герметичные звенья могут состыковаться, обеспечивая возможность человека проверить все системы.
So this is the stationary configuration of the train while it's on a just stop. When the hermetized and pressurized modules are connected together, and some other non-piloted platform can operate separately.
Ну, значит, две условности мы приняли в этом фильме, а именно мы считаем, что все происходит на ровной поверхности.
Two conventions are admitted to this video. You see, we assume that the surface is flat and horizontal.
И вторая условность, мы не считаем Солнце, ну просто чтобы было видно. И это сделано для того, чтобы облегчить создание фильма.
And we do not take into account the sun position and the shadows in order just to simplify the making the movie.
Ну, разработку мы проводим, конечно, с учетом того, что движение будет на сложном рельефе и освещение будет различное. Спасибо за внимание.
Of course, the design takes into account all these just shortcomings.
Большое спасибо. Thank you very much. Only two short questions because we already overtiming. Please, Lev Matveevich.
Я по-русски скажу. Михаил Иванович, спасибо за очень хороший доклад, но у меня вот беспокойство, все-таки ваши вот эти последние модели, они предусматривают присутствие человека, и, на мой взгляд, без такого толстого слоя свинца на крыше, в общем, будет опасно в нем ездить. Вы не учли вот эту радиационную нагрузку, которая на Луне очень велика, просто солнечной панели мало будет закрыться. Что вы думаете?
Ну,
The question was about the protection from radiation and.
Значит, ну что, я могу сказать, что я показывал этот не фильм, всю презентацию, все наши разработки Сергею Константиновичу Крикалеву. Да, эти замечания были, все. Конечно, над этим надо работать, но это уже как бы и не наша часть. Наша часть — самоходное шасси и интеллектуально-мобильная платформа. Ну, 18 тонн. Какой? Вот модуль лунный. Ну, я вам скажу, вот сейчас на МКС последний модуль «Наука», он весит 22 тонны. Ну, так примерно.
This is a discussion about the protection and the possibility from engineering approach to counter this threat from the radiation using some lead or other protective material which add more mass to the platforms.
Yes, thank you very much. And unfortunately, we have no question, no time for your question. It will be possible during the coffee break. Is it absolutely necessary right now?
Московский государственный университет. механика грунтов, основания и фундаментов. Я хотела бы узнать, как вы себе представляете уплотнение реголита, рыхлого грунта с очень переменной толщиной и достаточно больших площадей? И как вы собираетесь увеличивать основные параметры их прочности, угол внутреннего трения и сцепления, учитывая особенности лунных грунтов?
Well, the
Спасибо.
question is, how are you going to make the soil is regolith more stronger on the lunar surface?
Спасибо. На луноходе-1, вы знаете, был специальный прибор для исследования физико-механических свойств грунта. На нем проводились эксперименты по оценке уплотняемости грунта и увеличению прочности его.
During Lunokhod mission, Lunokhod had a special device to measure the mechanical property of the soil and its ability to get more dense, to be compacted.
Цифры, вот исследования показали, что уже при втором нагружении прочность увеличивается вдважды. Несущая способность увеличивается.
Investigation during those mission showed that the second time that we compact and press the soil, the strength of the soil increased 2 times.
И здесь единственное, что можно сказать, что действительно вот эти исследования были проведены в основном в морских районах.
What we can say in excuse is that those investigations were made in marine areas of the moon.
Где и естественная прочность грунта лунного реголита, она достаточно такая близкая по цифрам. Выбросов больших не бывает.
Where the variety of the soil parameters of the regolith are more or less equal, and there is no much variation in its parameters.
На других участках, да, возможно, другие. Надо, конечно, дополнительно исследовать вопрос.
So anyway, we need more investigation, more research on this question.
Михаил Ильич, спасибо большое вам за ответы на вопросы,
Спасибо.
за доклад. Особенно спасибо за кино. Thank you very much for your presentation, for answers, and in particular for movie. We have small problem now. Ivan Agapkin was late, and we spent already his time. So I give you 5 minutes. Please, your talk only 5 minutes, because your time is already used. So Ivan Agapkin will speak about selective laser melting for lunar soil analysis. Unfortunately, 5 minutes. And I remind you that next speaker will be Maya Dichkova instead of Lysenko. Lysenko will be the last in this session.
Hello. Today I will tell you about application of selective laser melting for lunar soil analog. So back to the second half of the 20th century, both USA and Soviet Union created lunar-based projects but at this time it was too expensive, too complicated technologically. So today, heavy vehicle by NASA is offering price for 1 cargo kilogram to the moon surface like for $75,000, and Space Falcon X9, which is using reusable launch system, is offering to drop this price to $3,000 per kilogram. However, it's still expensive for humanity, and that's why in situ research utilization concept is offering to use lunar regoliths as a prime material for developing infrastructure at the moon surface. And additive manufacturing is the most promising technology to achieve this goal. The most common methods, lot of them, but the most popular is cement countercrafting, sterile lithography, binder jetting, and the last 3 methods, I will tell you a little bit more about it, because these methods is concepts that they know using additional materials like polymers or some binders. So selective laser melting based on laser energy, which is sinter or melt regolith particles layer by layer to create 3-dimensional parts. Advantage of the method is high compressive strength, rapid and accurate method, feasible for printing complex shapes objects. Disadvantages: energy consumption, especially if we are comparing it with microwave and solar light energy, and porosity issues. Microwave sintering is based on unique ability of lunar regolith heating up and sintering or melting due to microwave irradiation. This method is interesting that it's only one which was tested on real regoliths on the samples from Apollo 17. This method interesting advantages: rapid heating of huge volume of material and deep penetration, low energy consumption comparing with laser, but disadvantages: heat distribution challenge, equipment complexity. Solar light sintering, one of the most promising methods, using only solar energy, so it's consuming less energy, and experiments even from the Earth was reached temperature higher than 1000 degrees, and print speed was higher than 2 millimeters per second. And 2028, Chingye 8 is planning to carry out this experiment at moon surface, and they choose selective light sintering method. So advantages: rapid production, extra low energy consumption, consuming. Disadvantages: its dependence on weather conditions, heat distribution challenges. So for us, we have to developing lunar soil analog for purpose of sintering or melting. Terrestrial, the most similar to lunar soil terrestrial material is volcanic ashes. So we have studied different samples from Kamchatka Peninsula, from different volcanoes, and preliminary research showed us that Talbachik sample is the most similar to lunar soil. Detailed research shows us. We said the prime requirement for our lunar soil analog is the most limitation of mineral and chemical compositions. So in mineral composition, we can see that Talbachik sample placed like medium position between Mayer and Highland average regolith composition. It's also very close to Apollo 14 samples. So we are considering our Talbachik sample like a mixed composition lunar soil analog. So it's very important to imitate glass content for sintering experiments, because glass content has lower temperature of liquid. If we compare chemical composition, we can see that Talbachik sample has more content of silica, but it still remains in mafic range. So we consider it quite appropriate sample. We choose selective laser melting experiment. actually because it was only one available equipment for us. So we are more than welcome to any collaboration. Yes, and selective laser melting, they use quite not modern equipment, and requirement was to make the strongest detail using less energy and time. Was developed piece measuring 1442 millimeters. Setup was printing speed 6 millimeters per second, power 50 watt, and we estimate for our detail micro hardness. In this final table, we compare different researchers with us, with ours. We can see that power is usually close to 50-60 watts. Values of micro hardness average like 600s or 700s. We're considering our attempt okay, and we are planning to future research. First of all, to make more complicated detail and to measure compressive strength and compare it, which is very important. And also it's essential experiments under vacuum and microgravity conditions. Thank you for your attention.
We have unfortunately no time for questions to Ivan. It will be possible to speak with him during the coffee break. Maya Dichkova, please. She will speak about another approach for lunar exploration, how to land. We already listened how to move over the moon, how to make regulate printing with laser. And now Maya will tell us how to land successfully using optical information about the surface.
Good day, everyone. My talk will be about some hazard avoidance using the optical images. As you can see that we now have a lot of data provided by Lunar Reconnaissance Orbiter, which has a narrow-angled camera on it, and thanks to that camera we have really good coverage of the lunar surface and a really high spatial resolution. So narrow-angle camera can do a stereo imaging of the lunar surface and from different orbits. And thanks to that, we can have really good details on the lunar surface, a really high spatial resolution that equals around 1 to 2 meters, and that is the best spatial resolution on the lunar surface by far, and that is the best data that we have. Unfortunately, the coverage of the stereo observation of the south polar region of the moon, as you can see here on the right, is really low. So red rectangles show the area that are covered by the stereo observations. And the coverage is really low, unfortunately, but it's the best that we have so far. We hope that we will have good coverage of the lunar surface when we have our Luna 26 mission that will image the lunar surface. But for now, we have the images that are shown here. So for our analysis, we used the image, the first image was the territory of the Luna 25 landing site. Main landing sites, it is located here to the north of Boguslavsky crater. And for comparison, we used two other stereo models, and they are located a bit to the north on the 50 degrees of south latitude. So for our analysis, we used three stereo models, three digital terrain models, and you can see here from on the right side of the slide, it's marked with A, it's north of Bogoslavsky crater, marked with B is fresh crater inside the Hanna crater, and in C you can see the part of Brisbane crater, and the last two are located on the 50 degrees latitude in the south, kind of south polar region of the moon. Our goal was to investigate the relations between the optical imaging and the topography of the lunar surface. You can see here that the A image that is located to the north of Bogoslavsky crater is rather smooth compared to the other two. For example, in B you can see the fresh crater, and it has different albedo characteristics, so you can see that the part of the image is really bright and the other part is really dark, and it is not always connected with the topographic characteristics. So we have albedo that makes it more difficult to see the topography on the optical images. So in principle, what we wanted to explore is that the relation between the topography and the brightness that is shown in the image. So usually optical imaging is used for hazard avoidance, and we should analyze the relation between the dangerous topography on the moon surface with the brightness that we can see in optical images. So, for example, if we have a flat surface, it will be shown in moderate brightness in the image. So, in case of the sun being up in the sky, so the altitude of the sun is rather high, so the flat surface appears rather bright. And in case, for example, if in case of the low sun, the most bright territory will be that one that have a high value of slope in the direction of the sun. So the problem here is that for different sun altitude, the method that we can use for hazard avoidance may be different, because different surface will appear dangerous in terms of brightness. So our ideal surface for landing, of course, is a flat surface that has no slope, or slope lower than 7 degrees, for example. And also we want to see no variability of the surface. So the surface should be flat and no variable, so it should not have roughness of the surface. And so it seems to us that we can see in optical images, we can see in the optical images the roughness of the surface, also not only the slope that dependent on the sun position. So how now we see the landing condition that we used in our analysis. So on the right you can see the landing area that we assume to be 20 to 20 meters, because we have the spatial resolution of the digital terrain models that provided by narrow-angled camera on the Lunar Reconnaissance Orbiter. So the spatial resolution of the digital terrain model is 2 meters. So we presume that the landing area should be around 20 meters and consistent of 10 pixels of primary resolution. And let's assume that we should analyze the surface with the optical image from some height up to the landing site, and let's assume that we can perform a move with our spacecraft. So the maneuver should be around 100 meters. So if we just land in the point that is in the center of the image with the right point, so we can land right here and do nothing, and we can perform a maneuver. So we can move from the initial central point to the landing area that is that seems to us safe, considering the optical image that we can make from the height of about some 100 or from first hundreds of meters. So how we should analyze this surface? So you can see in gray tones, for example, a landing area of the size of 20 to 20 meters, and the initial pixel initial resolution is 2 to 2 meters. So this pixel, for example, has a size of 2 meters. And we can see the relation of the brightness of the pixel to the topography characteristic. So each pixel in the optical image has its brightness, and we wanted to see how it's related to the slope of that pixel that we calculated on the digital terrain model. So you can see in the right part of the slide on the top the kind of relation between the brightness of the pixel and the slope of that pixel. So you see here that we can choose the brightness of the optical image to be corresponding to the low slope. You can see here that the central part of this plot of around 55 percentile or 50 percentile, so the central part of the distribution of optical brightness in the image, it corresponds to the best, to the lowest slope in the terms of topography. So if we, and it's fair for the image with the high sun. So the height of the sun was 20 degrees for this analysis, and you can see in the lower part of the right part of the slide that it's a relation between brightness standard deviation and roughness. So we used the vicinity of the pixel of 3 to 3 pixels, and we calculate the standard deviation of the brightness, and we related it to the roughness of the same vicinity of 1 pixel. So roughness in our analysis was the dispersion of vectors that are orthogonal to the each pixel. So the dispersion of these vectors is the roughness of the surface in our terms, and roughness is in degrees. And you can see here that the lowest standard deviation of brightness corresponds to the lowest roughness, and that is the part of the image. So we want to land. So in the analysis of the brightness, we see the two conclusions. That the first conclusion is that we need to use the brightness that is in the central part of the distribution of brightness. So we don't want to land in the most bright and in the most dark areas, obviously, and we want a lowest standard deviation of brightness possible, so we can land on the safe area. And that is fair for the high sun case. You can see here the two distributions, and the left distribution corresponds to slope distribution in blue line. You can see the distribution for the areas, for the landing areas. If we do not perform any strategy and we don't use optical image, we just land in the central point of digital elevation model that covers of around 30 kilometers to 10 kilometers, and from that landing cases, we see the blue distribution. So we can see that in the dotted and dashed lines, you can see the 15 degrees of slope and 7 degrees of slope, and that considered dangerous slope. And you see that the pink distribution, pink dotted distribution, show the case in which we use the optical image and we consider the brightness of the pixels to choose the best possible landing area. And you can see that distribution is shifted to the left, and so the part of the distribution corresponding to the dangerous slopes is lower than the original distribution if we don't use any optical image, any hazard avoidance. And on the right part of the slide, you can see the same distribution for the roughness of the territory, and you see that we, with optical image, we also can lower our risks, and we can choose the better territory to land. And this case is for the low sun. Again, thanks to the narrow angle camera, we have different images for different sun conditions, and we analyzed the image for the 5 degrees sun altitude, so it's a low sun in the morning and it's probable conditions to real landing. And you can see here that the distribution, the pink dotted distribution corresponding to the strategy of using optical image to choose the best landing territory is shifted even more prominently comparing to the high sun, and you can see that we can actually really low the risk of bad landing and to choose the territory that is safe. We performed this analysis for many cases. For the cases of 2 digital terrain models, it's for north of Boguslavsky, and for 2 difficult terrains with different albedos and different bad, let's say, bad topography, and for 2 cases of high sun and low sun. High sun means around 20 to 30 degrees of sun altitude, and low sun corresponds to 5 to 8 degrees of sun altitude in the morning. So you can see that the percents, it's the percent of dangerous territory with the slopes bigger than 7 degrees or greater than 15 degrees. That is critical for the mission. And for roughness, we choose the criterion for 3 degrees of roughness should be the dangerous criterion for landing. So we can see that the percent of the territory that is unsafe is lowering if we use high sun or low sun optical image to perform hazard avoidance. And the part of the territory that remains dangerous is shown, and you can see that it lowers from 1 to 0.8 in case of Boguslavsky high sun, or in some cases, unfortunately, for example, for digital terrain model in crater Brisbane Z, we can see that the territory that is, in case of roughness, that the dangerous territory being 30% of the area even goes high up to the 4%. So the actual optical imaging, the actual hazard avoidance using optical image worsen the condition of landing. So we see here that performing the hazard avoidance based on optical imaging may be controversial, so we should very carefully explore the territory that we want to land and use the images of high sun, of low sun, of different angles of the sun, and only then we can use optical imaging to see if the territory, dangerous for landing or not. So, except of that problem, we have a problem of noise. So we should really calibrate the camera very good, because very well, because if the camera not working right, so it will worsen the results. If we do not know the shift of the brightness of the image, if the different pixels of the optical image has doesn't have a calibrated brightness, the results of optical imaging may be not so good. So you can see here the case of 30% of the noise added to the brightness of the images, and it worsen the case a bit, but not much. So if we are in the a small amount of noise in the image, it's still useful, but if we have a large noise, it will be critical for the hazard avoidance with the optical image. So to conclude my talk, we checked the possibility of using optical imaging for hazard avoidance in terms of topography for slopes and roughness, and we saw that the risk of unsuccessful landing is reduced, and in sometimes almost by 2 times. But also we saw that in cases of different topography and in different sun conditions, we cannot use optical imaging, or we should explore the territory very well before we can use the optical imaging, so that optical imaging won't worsen the situation with the landing. And of course, the calibration of the camera is critical to eliminate the effect of different sensitivity of the neighboring pixels, but still it's a good approach, and the main conclusion is that we should land in the territory the more precise way as we can. So the more precise the way we land, the better the conditions will the camera provide with optical imaging. So it's kind of good method to provide a safe landing, but it still needs a lot of exploration between we actually perform that on the landing mission. So thank you for your attention. That's all for me.
Thank you, Maya. Unfortunately, we are still a little bit over time, so I suggest, Maya, with your permission, we will not ask you any questions this time, and we go now to the next presentation, but you will be asked. Next presentation now is about the investigations, about observations, which we want to do on the moon after successful landing, which will be provided by instrumentation which Maya described. So Andrei Shugarov will speak with us about ultraviolet small telescope with high level of development. Please.
Dear colleagues, in my presentation I will give you information about our current activity between 2 teams from INOSAN and from National Astronomical Observatory of China about the concept of small lunar-based ultraviolet telescope. As you know, a few years ago, China and Russia signed agreement about International Lunar Research Station, and one of the objectives of this agreement to define the ILRS-5 mission, which supposed to build astrophysical telescope on the moon. For several years, several teams from Russia and China works together, and preliminary we can offer 2 concepts for ILRS-5 mission. The first concept on the left is about relatively large aperture 60 centimeter or 1 meter moon-based universal UV optical infrared telescope. The second concept is about to build a very wide field of view multi-aperture ultraviolet telescope. More details about these concepts and about science will be given by talk Van Huijan after the coffee break. Please do not miss her talk. I just may quickly say that the first concept is a large telescope with a set of scientific instruments like cameras, spectrographs, and maybe some other instruments. This large telescope will be suitable to solve many astronomical, astrophysical objectives. And the second concept is focused on time domain astronomy in near UV region. This mission will be suitable to give the first in the world high cadence 10 minutes all sky survey of the sky to search for different transient events like merge of neutron and black holes, supernovas, and so on. Before to build and to launch such expensive telescopes, we considered to build a pathfinder or a prototype of each options, and we limit us as for a budget of 5 to 10 kilos to offer this small telescope for upcoming missions. Firstly, speak about prototype of a large aperture telescope. As you see on the right, the prototype will be a compact classical two-axis mount telescope with aperture of about 10 centimeters. By this prototype, we can verify several technological aspects which are important to build a large telescope on the moon. For example, the question how to protect astronomical optics from the dust, and we may try different methods how to protect and maybe how to blow up some dust from the optics. Also, we are worried about stability of the moon lander on the moon regolith because it is soft and mellow, and if we want to build a large telescope, how about its stability at subarc second level? Our small prototype may try to get real experimental data about stability of the lander on the moon with subarc second level. Also, we may say that moon is not ideal place for astronomical observations because of the difficult scattering light conditions from the sun, from the moon itself, and thermal conditions on the moon is also not perfect. Such a small telescope will be useful to verify these two aspects. To build astronomical telescope on the moon, we want to check unique methods which are accessible only if we put telescope on the moon. For example, we may offer to perform synchronous observations of near-Earth asteroids in triangulation mode by two telescopes, one from the moon, another from the ground. It will help us to determine the orbit very fast. Also, we are thinking about asteroids observations close to the sun. If we put a solar blind detector, we may observe Earth's exosphere from the moon, and also we are thinking about occultation observations of some solar system objects by the crater hill or the moon surface in occultation mode. Among other scientific objectives for such a small telescope, we may present this long list. I think most interesting will be to observe different targets in target of opportunity mode. We understand that the aperture of our telescope is small and we will have only several filters, but nevertheless this telescope will be useful for some astrophysical research. And also we have idea to offer such a small telescope as additional payload to any other missions to the moon to continue
to begin a continuous international observation campaign from the moon. Here you see a draft drawing of this telescope. We choose a classical alt-azimuth mount with a classical worm gear because we don't have requirement to build a very fast mount. Our optical design main driver is to build the telescope of small aperture but with best possible angular resolution. That's why we choose the long focus optical scheme to provide close to diffraction limited image quality at far UV. Telescope will be operated in a target mode. It will be not a survey telescope. Here you see an optical scheme. As you see, it is very compact. The size is about 15 centimeter, just slightly larger than a CubeSat, but it allows us to build a telescope with 1 meter focus length to achieve quite reasonable resolution of 2 to 3 arcsecond. We suggest to use modern CMOS detector with very low readout noise and special advanced UV technology available to increase sensitivity in UV region. Why we speaking about UV? Because this region is not accessible from the ground, and UV region allows us to achieve better angular resolution. In addition to UV, also this detector will operate in optical wavelengths. We suggest to put several fixed filters on the detector, directly on the detector, several UV filters, and maybe 1 or 2 optical ones. Also, we have another approach how to build two-axis mount for a moon telescope. Now we see a very rapid development of the laser communication technology at low Earth orbit, and we already have many available solutions from the shelf that already flown. They have technological readiness level of 9. For example, here you see a photo of the laser terminal of 7 centimeter aperture. It is available like a commercial product, and the parameters of this mount well suitable for astronomical telescope. The tracking accuracy is about 1 arcsecond, so we may use this mount and to modify the telescope, to install astronomical detector, to modify it to operate in ultraviolet region, and on the bottom you see some parameters which are accessible with this concept. About second approach to build telescope on the moon, you see our second approach to build a multi-aperture telescope to perform the whole sky survey in near ultraviolet. And about prototype, we have idea to use the largest available star tracker with aperture of about 80 millimeters and field of view about 5 degrees. It is a commercial product, and this star tracker may be modified to operate in near UV. The expected mass will be about 5 kilos. It is a single channel of our future multi-aperture telescope. We have option to mount this single channel on simple one-axis mount. It will allow us to have more flexible observation program with only one tube. So this is a possible way how to build a prototype for such multi-aperture telescope. So the conclusion and prospects. Now we are working on an idea how to offer a joint Chinese-Russian small additional payload for upcoming missions, for example, for lunar missions. We found several options how to build a small 5 to 10 kilos telescope relatively fast using off-the-shelf components with some small modifications, and This prototype allow us to prove many technical parameters to build a future large ILRS telescope, and also this small telescope will allow us to begin astronomical observations from the moon. Thank you.
Thank you very much. Maybe just one question, if necessary. There are instruments which just will be very nice at both poles to make the global all-sky observations.
Yes, to have less problem with electricity and thermal condition, it's better to install such a prototype on the south or north pole of the moon.
And South Pole give us the center of our galaxy. So, no questions. Thank you very much again. And the next presentation before the coffee break will be from Habibullah Abdusamatov about just asteroid comet hazard avoidance program. Please. Please, you may start your presentation.
Быстро, вы не получается. Как мне включить?
I'm not sure that we have good opportunity for
Давайте,
presentation.
нажмите. Ага. Все. Спасибо.
Yes, please, you may start.
Potentially, одну минуту, подождите. Potentially dangerous nearest asteroid and comets, especially those approaching zeros from the side of the Sun, constitute the largest threat since they are more numerous than massive bodies and appear unexpectedly. Therefore, they are still the least studied celestial bodies and those which present the greatest danger. Continuous coordinate photometric monitoring and research of the asteroid comet hazard throughout the celestial sphere require the creation of long-term stationary space platform precisely on the surface of the moon facing the Earth. As an ideal, highly stable space platform for monitoring a system of astronomical telescope for long term and in the nearest future constant continuous all-sky survey in future, the moon also has spectral advantages for observing the near-Earth asteroid and comet, including its continuous lifetime and unequal perspective. However, the observation of the astronomical object from the moon surface in the conditions of the lunar daytime continuously during more than a half of the lunar day until recently remained an unsolved problem. They have become possible due to our invention, patent of the Russia, new method of the study, continuous coordinate photometric monitoring, and research of the asteroid comet hazard throughout the celestial sphere due to the specially developed system of the robotic optical twin telescope. Therefore, since 2012, at the Pulko Observatory by us has been actively developing the Lunar Observatory, a system of two identical special optical robotic twin telescopes with sliding wizards with primary mirror diameter 300 millimeters in short solder in the dust protecting cup, protecting from charged lunar dust particles. The lunar platform that we developed consists of a single system of two modernized spatial optical telescopes working sequentially as a single telescope only in the daytime at the places where they are installed continuously during 100% of the lunar day in the automatic mode according to the single science program of observation of stellar field patent of Russia. Twin telescope will be placed along the equator on the opposite edges apparent surface of the moon at the latitude plus minus 81 degrees and at the equator latitude. So the twin telescope working sequentially and taking turns in automatic mode as a single telescope examines the celestial sphere under daytime condition continuously during 100% of a lunar day. In order to protect the mirror from the surface-borne particles of charged lunar dust, Soter is mounted in the central zone of the special cup, which displays the shape of a turning truncated cone. The cup is made so that it may be placed above a relatively smooth area with an incline up to 7 degrees on the lunar surface with its upper level at the height exceeding 1000 millimeters above the surface. The cup features supporting legs with the vertical height of about 300 millimeters. They are calculated taking into account the total mass of the set and all possible overweight, including those occurring in the course of landing of the set of the moon's surface. To protect the telescope mirror from the surface-borne charged particles of the lunar dust, the outer surface of the cup and the entrance pupil, as well as the surface of the mirror, are covered with electrically isolated conducting envelopes connected with the electrical power unit placed in the cup. The electrical power unit displays electric charge with the specified frequency of the polarity inversion, in particular depending on the alternation of day and night patterns of the Russia. General view of Soter in the dust protecting cup in a longitudinal section, telescope lens hood is not specified. Main optical characteristic of three-mirror telescope Soter: entrance pupil 230 millimeters, radiation detector 32 millimeters, working field of view 2.2 degrees, spatial resolution diffraction. Optical design Soter with anti-illumination hoods. Longitudinal section of Soter in the dust protecting cup and its overall dimension. The telescope tube is located at height of 1,175 millimeters. The diameter of the dust protecting cup equal 1,170 millimeters. The modernized azimuthal mounting of Soter robotic telescope along two axes provides any necessary tilts in azimuthal direction of the telescope tube and a needed angle which makes it possible to observe astronomical objects over the entire celestial sphere above the lunar horizon up to the altitude 90 degrees and for all azimuths. To protect the length of the telescope from the solar and Earth's radiation at the angular separation of more than 15 degrees, the hood will be used. By shielding an entrance pupil from solar and terrestrial radiation with a hood, the twin telescope can also detect asteroids and comets approaching the Earth from the side of the Sun at an angular separation exceeding 15 degrees, thereby contributing very substantially into planetary defense. Continuously during 100% of the lunar day, the system of twin telescope sequentially taken turns only throughout the daytime carry out coordinate photometric monitoring and study of potentially dangerous near-Earth asteroids and comets, especially those approaching the Earth from the side of the Sun, and also supernovae and novae with a resolution of 1 arcsecond pixel. Over the total broad working field of view 2.2 degrees, over the entrance spectral range 0.22 micron in its 3 individual broad bands. The very slow axial rotation of the Moon will significantly increase the accuracy of positioning with the optical telescope, which will make it possible to significantly lengthen the time of exposure and consequently significantly increase the number of used stars and identified asteroids and comets. The system of SOTER continues during 100% of the lunar day, sequentially will be able to provide a complete survey of the stellar field of the entire sky with the exposure of 60 seconds for the time of the 360 hours, taking into account the semi-diurnal axial rotation of the Moon. An individual survey of an area of the sky around the Sun at an angular separation exceeding 15 degrees will carry out for every 36 hours. At lunar night time, the telescope system will continue to observe the Earth for more than 94% of lunar day. At lunar daytime, telescope system will continue to observe the asteroid, comets, supernovae and novae during 100% of the lunar day. Functioning of the system of the SOTER depending on the change of lunar day and night. The system of SOTER telescope will be able to detect bodies with the diameter above 10 meters, the most interesting from the point of the asteroid and comet hazard. The system of the SOTER telescope will become a professional space patrol carrying out the early detection of near-Earth asteroids and comets, especially those approaching the Earth from the side of the Sun. There are no other optimal ways or alternative non-lunar method for continuously monitoring throughout the celestial sphere for study of the most important problem of the asteroid comet hazard. A sliding wizard and a charged ring protect the optical element from lunar dust and its electric charge patterns of the Russia. A specialized dust protecting cup of SOTER will be adopted as a landing module with soft landing engineer to install the telescope on the required area of the lunar surface. Soter with lightweight mirrors in the protecting cup without the solar panels, and soft landing engineer will have the mass of one set less than 100 kilogram, the dimension less than 1,500 millimeters, the required electric power much less than 20 watt. Soter will be equipped by single or mosaic CCD matrix, 8,000 to 8,000 pixels as a radiation detector for surveying the entire sky. Soter telescopes are fully automated and don't require the creation of a lunar base and the participation of cosmonauts during their installation and maintenance in the future. To this end, a successful experience of mounting in 2013 of the China Lunar Base Ultraviolet Telescope, analogous in all technical parameters, without a landing unit and without the assistance of cosmonaut may be used. Our complex of the Soter on the lunar surface. Any part of the celestial sphere is accessible for observation by this system of twin telescope located in the equator, protected by 4 patents of the Russia. Zverev-Krasnogorsk plan, after careful study of all the scientific and technical equipment of the Project Lunar Observatory, issued an official conclusion on the technical feasibility of this project. The objectives and tasks content of scientific payload, ways, and techniques of implement of the developed by us Lunar Observatory have been fully and completely supported and accepted by the Research Institute of the Roshydromet and for Research Institute of the Chinese Academy of Sciences, and published on Journal of the Indian Society of Remote Sensing in 2024. The Pulkov Observatory of the RAS, within of the two scientific goals of the International Lunar Research Station, Universal Way, Sun-Earth relation, in planning to implement the Lunar Observatory in alliance with the Research Institute of Roshydromet and the Chinese Academy of Sciences, in accordance with the federal law of the Russian Federation of June 12, 2024, number 128. Conclusions. The system of optical twin telescope will be continuously carrying out coordinated photometric monitoring in study of potentially dangerous near-Earth asteroids and comets, especially those approaching the Earth from the side of the Sun, and also supernovae and novae throughout the celestial sphere. Soter telescope of Lunar Observatory will be able to detect bodies with the diameter above 10 meters, the most interesting from the point of the asteroid and comet hazard. Lunar Observatory will become a professional space patrol aimed at early detection of near-Earth asteroids and comets, especially those approaching the Earth from the side of the Sun. Obviously, the complex of tasks solved by the lunar observatory will remain extremely important in solving fundamental scientific and applied problems throughout this century and beyond. Therefore, this system of twin telescope of the lunar observatory should be updated every 20 years with a new modernized system with an extended science problem to carry out continuous research. Many thanks.
Yes, Dr. Abdul Samad, thank you very much for your presentation. I may say that unfortunately the listening was not perfect, but it is very good that you have a lot of patents and you have a publication, so interested people may be able to read details of your device, of your instrumentation. Now we are finishing the session before the coffee break. Thank you everybody for participation, in particular speakers for presentations. We have joined again after 20 minutes to continue our part of this session. So 4:20, please be here. Thank you.
Можете, пожалуйста, отключить свою презентацию, закончить? Будьте добры закончить шеринг экрана. Всё.
We are starting our session in 1 minute. Flight is ready for immediate departure. I'm inviting everybody, sit down, please. So before the regular session, we have 2 other presentations. Continue our observational part, I would say, on the moon. Not on the Earth, but on the moon. So I invite Professor Huan Wang to continue the subject of ultraviolet optical and infrared telescopes on the moon. I think that we will have a remote presentation. Oh, you are here. Okay, great. So you will have 20 minutes.
Okay, thank you. Good afternoon. I'm Hui Juan from National Astronomical Observatories, Chinese Academy of Science. It's my honor on behalf of our international research group to give us a brief introduction about our recent progress on the lunar-based UV optical IR telescope for the International Lunar Research Station. Our collaborative groups, including INASEN, Peking University, and the University of Science and Technology of China, Zhejiang University of Technology, and several other groups. Thanks a lot for our committee to give us this chance. Here's the outline of our talk. Several experts have introduced that advantage of the lunar-based observation. Yes, if we think that if the observation could do on the ground or by a space satellite, it's better that we don't do the observation on the moon because it's more expensive. But when we think about lunar-based observation whereas space-based observation, there's several advantages. As I have at the end have introduced, and I will just summarize is in several words. First is high precision. It's not only about the absence of the atmosphere, but also because the stable position of the telescope, because especially for the long explorer of the observation, some spacecraft may have problems with the stabilities. And the second aspect is long duration. Continuous observation is very important for the observation, for example, the exoplanets research. And the third one is the ultra-wide wavelength coverage. Here's a very picture that we are all very familiar about that. We could see that including the extreme UV, far UV, near UV, and infrared, we could perform the observation in such ultra-wide wavelength coverage. Okay, here's a concept picture. The lunar-based UV optical IR telescope, or the array, for the International Lunar Research Station is a sense-driven pilot prompted by our collaborative research group from Russia and China. And this picture has showed by Andele. And we have published a concept design of this telescope in 2022. So we will have a very brief introduction about our scientific objects. First is enhanced comprehension of evolution of a galaxy. We all know that a galaxy are the fundamental units of the universe, and the star formation rate is a key indicator to characterize the evolution of the galaxy. Especially the UV data are very important for the research of the star formation rate. Here's 4 pictures that show the sky coverage of a galaxy, Swift, XMMOM, and LUT. That we could easily to find that they have do very wonderful research work, but still there's some efforts we need to do. For example, the sky coverage and the detection depths and the precision. And so now there's no complete and uniform UV catalog so far. So our first scientific objects is to finish a dynamically update and complete UV catalog and study the evolution of galaxies, and conduct research on galaxy formation and evolution using all-sky ultraviolet samples, and create a map of galaxy evolution covering 80% of the history of the universe. Maybe you will ask why 80%, why not 70% or 90%? It depends on our budget for the mass and the power and the layout of the payload. If this number is calculated by the budget for a 1 meter level telescope, and here's in this formula, we could see that galaxies with XMMOM and LUT, there are filters, sky coverage, and the objects they have observed, and aperture, platform, and the countries, and it's published the year of the last copy. We could see that the largest coverage get by galaxy is about 77%. Okay. The second scientific objective is to get advanced knowledge of the high energy transient and variable events. Exploring high energy transients and variable events in the local universe is a very key point of the astronomical research. Currently, maybe one of the most ambitious plan is the UltraSight plan, which planned to launch in 2025. And this in the right part, there's a picture that shows the graphs that is the capability to do the survey of the sky. Especially in the UV, near UV band, here is UltraSight, and this is ultra-wide lunar UV survey. So we could do better. And we planned to complete samples of nearby supernovae of all kinds, and tidal disruption events. And the most important thing is to get the data in about 1 hour after its explosion. Okay. And the third one is to more profound understanding of habitability of exoplanets. We will explore the influence factors of habitability from a new and unique perspective, and explore the future habitable home for human. It means that we will consider about the magnetic activity of the host star. The EUV data is very important for this research. And the second thing we will consider is the small bodies, small objects that, for example, the comets, asteroids, and some NEOs. Okay, we will investigating the habitability of exoplanets based on space weather phenomenon and the influence of small bodies in the planetary system, and to open a new era of extrasolar space weather research. And by the way, we could discover NEOs in the direction of the sun to support planetary defense. And the last one is deeper insight into another Earth. The first exoplanets orbit a solar-type stars was discovered in 1995. We all know that the first exoplanets is discovered several years before this one, but this discovery get the Nobel Prize, not the first exoplanets, is because it's orbit solar-type stars. It's more, it have a high ability to support habitability worlds. But we know this exoplanets is not suited for Leo because it's a Jupiter-like exoplanets. Whatever. But currently, the number of the exoplanets have increased by order of magnitude by the survey of space-based telescopes such as Kepler, TESS, and so on. But terrestrial exoplanets in habitable zones are still rare, and so expanding the sample of the and in-depth study is still very important. But this research need long-term, multi-band, simultaneously and continuous observation. So the lunar-based is a very good platform for that. We not only do the observation in daytime, but also in the nighttime. That means we could do the observation continuously for a very long duration. So we will discover, we plan to discovering new terrestrial exoplanets in habitable zones. Okay. Here's a summary of the optimized scientific objectives. I will not read it again. Okay, I will introduce recent progress. During the past 1 year, we organized several ILRS, lunar-based astronomy observations and research seminar, including Russia, China, collaborative teams together, and also in China. And the second is research on methods for site selection for lunar-based UV optical IR astronomical observations. The last one is a concept, the optimize of the concept design of UV optical IR telescope. Okay. When we think about to build a telescope on the moon surface, what we need to think? Where is best position to build the telescope. So we have our group, our international collaborative group, have think about the visible sky distribution near the south pole of the moon. From the the top left to the right bottom, the blue area means the sky coverage of our telescope. So the perfect is the left top, and the worst is the right bottom. And on the right part is the position in the schematic diagram of the distribution of the skyline in the line projection map. And we also do the simulations of variable sky coverage in different latitude. So we only need to change the input sample that we interested to do the research. We could get the observation time and the sky coverage of the research. Here's our the observation duration of TICE actual planets planet candidates for just for a sample sample, and we could see that the right part is because we put this position in on the position of here. It's about 0 degree east, 8 degree south. We could put it on anywhere on the Earth's surface. Okay, this work have published. And the last one is a concept design of the ultra UV optical IR telescope and the array. Here is concept design of our collaborative group, which have published in 2022. And now we also, as this is a larger telescope, the diameter of the larger telescope is about 60 centimeter. And here we also do a concept design about a telescope of meter level. And when we think about to build the telescope array step by step, we could first to put a telescope with a large diameter and array with a small diameter but have a more wide field of view. We also have designed about the diameter, the mass, the layout of the payloads, and some other concept of it. Okay, that's all. Thank you very much.
Yes, Dr. Wang, thank you very much for your presentation. Please, we have time for questions. I have short questions. For this beautiful system which you described, how much electrical power would you need to operate?
Thank you very much. A very good question. This is a very important question that we need to think consider. Currently, for a 1 meter telescope, the power at least about 400 watt. Yeah.
Repeat again.
400.
400. Thank you.
Yeah. Thank you.
Please, another questions. Yes, please.
Thank you.
You are very right that there are many advantages to have the telescope at the moon, but there are also problems. Very big jumps of temperature and dust layer. Do you plan to somehow to counteract
to
them?
Thank you very much. A very good question. This is really another very important question that we need to think about. The temperature on the surface of the moon is very, it's very big. Yeah, changes. So we need to design the protector system to keep the temperature for this telescope. And the detailed designs we still don't have, but we just in the past years we have try to do several efforts on that because the progress is not so big, so we didn't report it currently, but maybe next year we could report it. And there's, by the way, there's several other aspects that we need to think about. I think you must more familiar than me. For example, the dust. I'm very happy that I heard several talks during our seminar that to introduce about the character of the dust. It's very important for it's really also very important for our telescope, because when the telescope is very small, it's okay. But when the telescope is big and it's moved during the observation, dust is a very important problem for the surface of the mirror and for the moving parts of the telescope. There's another key questions that we need to consideration, and there's several other things. For example, the impaction of the very small micro bodies. Thank you very much.
Yes, thank you again. We have to move on. Now we see how many infrastructure we have to build on the moon, and I invite the last speaker of this session, Anton Lysenko, please. You remember that we exchanged 2 talks, and he will return again to the 3D printing on the moon from regolith to provide elements for this infrastructure. And then we will go to the science on the Earth under the leadership of Mikhail Gerasimov about samples. Yes, please, Anton.
Good afternoon, dear colleagues. My name is Artem Lysenko, and today I will tell you the report about 3D printing of lunar regolith, testing physical conditions for implementation of selective laser melting technology. The aim of the work is to identify the best physical conditions of selective laser melting technology for creating volumetric products from lunar regolith. Recently, due to the return of man to the moon, many scientific groups around the world have been discussing and researching the issue of creating structural materials from lunar regolith. Over the past 1.5 decades, several technologies of this process have already been proposed. In 2019, our scientific group from the Institutes of Imash Ras and Iki Ras began work on the study of the process of creating structural materials from lunar regolith by the additive technology, namely selective laser melting. A big advantage of additive technologies is the ability to create samples of complex geometry for different tasks without changing the device of the installation itself. Additive technologies also have the... Yes, of course. Additive technologies also have the ability to easily change the melting parameters to achieve the best result. It is important to note that in conducting research on this topic, we are not working with natural regolith, but with earthly material Gabardia base, similar to lunar in chemical, mineralogical, and morphological composition. When preparing the simulant, we crushed and shifted Gabardia-based crumbs to match the granulometric composition of the powder with the composition of natural regolith. In the experiments, we worked with 3 different fractions with a particle size from 0 to 100 microns, as well as with 2 relative narrow fractions with a particle size from 0 to 50 microns and from 100 to 140 microns, made by us to increase the flowability of the powder. During the work on this project, we have already learned how to create satisfactory quality volumetric samples from lunar regolith simulants, having completed a full production cycle from studying natural regolith and creation our own simulant for our purposes, to studying the physical and mechanical properties of the obtained samples. A year ago, at this conference, we already talked about these studies and showed how different melting parameters affect the quality of the samples obtained. And now, after proving the fundamental possibility of create bulk products from lunar regolith using additive technologies, the focus of our work has shifted to more detailed experimental and theoretical studies of the search for optimal fusion modes to create samples of the best quality. As befits additive technologies, laser fusion of lunar regolith occurs in layers along the selected trajectory. The sample consists of overlapping single tracks. Therefore, the quality of the final sample is influenced firstly by the quality of single tracks, which depend on the density of the energy supplied to the powder, and on the fractionality of the powder. And secondly, by the amount of overlap of single tracks, both between adjacent layers and between tracks located in the same layer. During the experimental studies, about 860 single tracks were melted and analyzed. 8 copies of each of the 108 types differing from each other in a set of parameters. A general view of the substrate with 36 vertical tracks melted on it in pairs can be seen on the slide in the left figure. The analysis was carried out using the following method. Using a microscope, we created photographs of tracks that can be seen in the central figure in 8 different places along the entire length. Then we processed the photos and using a program written in the Python programming language, calculated the width of the tracks pixel by pixel along the entire length of the photo. For each of the 108 parameter sets, approximately 120,000 tracks width values we obtained in different places, which were then used to plot histograms of the distribution of this parameter. These histograms describe the quality of the resulting track. If the histogram is narrow, then the track turned out to be high quality and homogeneous. We also calculated the average width
the standard deviation, the number of places with powder spraying, and track break for each mode. We have named these parameters as a quality parameters. As a result of experimental work, we have constructed various graphs of the dependence of the above described quality parameters on the initial parameters. For example, the slide shows graphs on the dependence of the track width and the relative value of the standard deviation from the energy parameter of the ratio of power of the fusion power to the velocity of the laser beam with a powder layer thickness of 150 microns. The graph shows that the fractionality of the powder has less effect on the width of the track than on its quality. Such graphs were analyzed to develop recommendations for further research to find the optimal value of the overlap of adjacent tracks in volumetric samples. Simultaneously with the experimental work, a theoretical task describing the thermophysical process occurring in a regolith powder under the action of laser radiation was posed and solved. As a result of numerical calculations, graphs of temperature, dependence of depth, and different distances from the center of the laser beam at different time points were obtained. On this slide, you can see the animation of the temperature distribution in a layer of regolith powder with a thickness of 200 microns, located on a substrate of molybdenum cardierite after passing a laser beam with a diameter of 50 microns. The diameter of the laser beam was 15 microns, a power of 80 watts, and speed of 133 millimeters per second. The time is shown in right corner. The red line shows the boundary of the melt at a given time, and yellow line shows the final boundary of the fused part. In the process of comparing experimental and theoretical results, graphs of the dependence of the track width on the energy parameter at different layer thicknesses were constructed on the same axis and analyzed. The graphs show that the theoretical model repeats the experimental data quite well. Later, after some refinement of the theoretical model, it's planned to use it to calculate the width and depth of the melt region. Together with the experimentally obtained data on the dependence of sample quality of the overlap of adjacent tracks, we will be able to use the model to predict the optimal value of the distance between adjacent tracks and the layer thickness to create high quality samples for any sets of parameters without conducting experimental studies. This will reduce the resources spent and the time of our work in the future. Thus, as a result of the work on finding the optimal set of parameters for creating high quality samples from lunar regolith, we created and analyzed many single tracks, different from each other, yes, thank you. We also fixed the optimal values of fusion parameters affecting the quality of the sample. Developed recommendations for experimental and theoretical investigation of the distance between tracks. Developed a theoretical model of fusion of lunar regolith powder, which in the future will significantly simplify research work on this topic. Thank you for your attention. If you have any question, I will be glad to try the answer.
Anton, thank you very much. Please, I already see some hand rise, so please your question.
Okay, I've got a question. Could you please say something about the mechanical properties of the melted material you obtained in your experiments?
Okay. May I answer the question on Russian language? Thank you. Если я правильно понял вопрос, какие исследования проводились с объемными образцами? Механические характеристики. С объемными образцами, полученными в прошлых исследованиях, мы исследовали истинную плотность, объемную плотность, пористость, предел прочности нажатия и твердость. Какие значения мы получили? Да, сравнивали мы их со строительным материалом керамической основы, то есть с кирпичом, с аналогом, и мы получали твердость порядка 850 HV, и предел прочности нажатия мы получали порядка 16-35 мегапаскалей, то есть соответствующий земному материалу. Пористость у нас была разная, это зависело от параметров сплавления, но получали мы не менее 30%. То есть особо плотные образцы, когда они у нас получались, но они уже теряли форму, и мы не могли назвать их качественными.
Please, another questions, if any. Yes, please. We are approaching to the end of the session, so maybe just one more question.
Thank you for your presentation. It was very interesting. I'm curious about your... May I ask you content, plate glass content? Раз. Okay, thank you for your presentation. I'm curious about your lunar cell analog. May I ask you about glass content? Did you imitate this phase of lunar regolith?
Да, спасибо за вопрос. В лунном реголите действительно в небольшом количестве присутствуют немного особенные частицы. Это сплавленное стекло и какие-то дендритные основы, которые возникли в результате появления этого лунного реголита. В ходе наших исследований мы поняли, что этих частиц не так уж и много, и действительно в нашем аналоге, в Грабер-диабазе, этих частиц нет. Этим отличается наш используемый реголит наш используемый имитатор от лунного реголита. Но проведя различные сравнения их составов, мы поняли, что эта разница незначительна, что на технологию сплавления влиять не будет. Спасибо.
So, Artyom, спасибо.
Thank you.
We ended our session about science on the moon, and the continuation will be led by Dr. Mikhail Gerasimov about the lunar science on the Earth. And I would like to remind you that we will continue with the poster session. Poster session will be very rich. We have 15 posters, and each poster will be presented as a flash for 3 minutes. So please be ready for the poster session in this late afternoon. Thank you.
So we are starting our next subsession of Luna session, and it is called Lunar Regolith. So it's the first time I think we have a geochemical subsession within this Moscow Solar System Symposium talks, and it was inspired by the Chinese Chinese lunar samples which were given to our academy, and the starting of analysis of these samples resulted in the opening of this very small subsession. So the first talk in this subsession will be given by Svetlana Demidova, and the name of the talk is, the title of the talk is Unexpected Components in Chinese 5 Soil Sample.
Hello. As you know, last year Chang'e 5 soil sample was delivered to us as a part of exchange between China and Russia, and now we have a possibility to study it. And it should be noted that this soil sample was heavily studied last years, and a lot of data have been published already. And we focused on search and study of something unusual in these samples. The regolith contains the local rocks. In this case, they are basalts and their derivatives. But it always contains exotic particles which brought from far located areas. And here you see basalts and plagioclase grain. A large set of the sample comprise impact-induced particles which are presented here, and they are breccia, fragmental rocks, agglutinates. These particles contains a lot of glass and bubbles and different mineral fragments. This is just an impact glass fragment, and glass spherules which could be of impact or volcanic origin. We should mention what was done before us, and the main component, rock component of this sample are mere basalts of intermediate titanium composition, and these are the youngest lunar mere basalts. Their age is about 2 billion years. But besides that, there were found fragments of low titanium basalts and fragments of high titanium basalts. A small part of this sample comprise exotic particles, and there were highland rocks found, a fragment of magnesium anorthosite, and several small fragments of evolved rocks with specific texture, granophilic texture. A single iron meteorite fragment was found, and the variety of space weathering products which mainly formed during impact. And it was some rare and unique titanium phases, as well as copper sulfide, native copper, and iron cobalt alloy assemblages. We also searched something special. We have found 4 highland rock fragments, and they are all breccias. It means they are fragmental rocks, which contains plagioclase, these dark gray fragments embedded into mainly plagioclase, embedded into a matrix, and this matrix sometimes is glassy, sometimes is crystalline already. And the main feature of these rocks that the plagioclase is calcium aluminum silicate, is extremely calcium rich. It is pure anorthite. And we have studied this one rock in detail, and its chemical composition of the phases suggests that it could be related to the primary highland rocks of high magnesium suite. And it's important, but we will not focus on it now because these components are rare, but they are expected. But now we move to the unexpected. And we have found some special metal grains which have very unusual texture. You see, they are something like filamentous crystals of from 1 microns to 4 microns, and they consist of these hairs, metal hairs. And these crystals suggest very fast growth. And it's unusual to most metal grains which are present in the regolith, and they are shown here. And there are several sources of the metal in the basaltic regolith. First one is basaltic sources. The second one is meteoritical material, and the third one is nano-sized iron particles, which are formed because of interaction with solar wind. And you see that the spectrum, they are pure iron. Oh, I forgot. In one case, we have found that this filamentous crystal is attached to the iron sulfide troilite. And previously, this metal sulfide association was studied in detail. I have shown here the papers which are devoted to this subject, and they are present. Metal sulfide fragments have different ratios of metal and sulfide, and they are present in impact glasses. And you see here it forms spherical particles, spherical objects, and even some chains of these spherical objects. And we have found that these filamentous crystals sometimes, not always, but sometimes, they are related to this metal sulfide spherules. And here you see this first stage of growth of this metal grain. And here you can see it grows up, and we have already filamentous, some starting point of filamentous crystal. It is thought that metal sulfide droplets are the products of liquid immiscibility in the impact melt. And the most surprising thing that this metal sulfide association sometimes contains magnetite, and magnetite is a mineral widespread in terrestrial conditions, but not widespread on the moon, because magnetite is an iron oxide which contains oxidized iron with degree of oxidation 3+. And this is a loose fragment in the regolith, but recent paper, last week probably, they have found this association attached to the ilmenite glass, and the authors and co-authors, they suggested that iron metal was oxidized because by oxygen from this ilmenite melt. Ilmenite is a iron titanium oxide. And but it should be noted that magnetite, it's not the first find. Magnetite earlier was found in Apollo 16 Brescia, and it is in close association with troilite. Magnetite is blue and troilite is red. And Joy and co-authors, they suggested some reactions with participants of water and CO2, and the possible oxidation agents they suggested to be low temperature volcanic gases, or impact-induced gases, or decreasing products of regolith containing volatile components. And it should we should not forget that Chang'e 5 is the landing site of Chang'e 5 is situated most close to the polar region among all these landing sites. And our unexpected component, we have found iron oxide. You see the spectrum, which contains no sulfur as previously one, and it has very unusual form. As you see, this is a fragment of previous spherules, and the size of this object is about 40 microns, and it means that the whole spherules was about 100 microns. And of course, it has very interesting texture. All these small crystals are from 2 to 4 microns, and they have smooth octahedral form. And we think that this is magnetite because octahedral form is common for magnetite. And besides that, these small crystals are organized and also in octahedron facets. And this fragment has very similar texture to the magnetite rhomboid crystals from terrestrial limestones. Rhomboid crystals are very rare component, and not component but crystal form for magnetite or sulfides, and it forms when some change in reduced oxidized conditions happens, or some changes in temperature. And of course, the first thought was that it could be contamination. But when we checked these tiny debris on surface of this grain, we have found that this is X-ray maps, and all these fragments are typical mineral phases of the basalts. Then we turned this grain to the other side, and we have found that on the surface of this chip site we have these tiny splashes of glass, and the glass some areas, and that means that this fragment was on the moon. Another interesting feature that the central part of this grain contains these some skeletal crystals, and it means that it was grown in open, not an open, but in a cave. It means it was a hole here before, and it's also consistent with rhomboid type of crystal. It's the fine texture of these grains are also very important, because you see this something like steps, and it means that some rather slow growth of the crystal was. And we start to looking for where these types of crystals could be formed, and we have found that such magnetites of rhomboid form or something like plaquette crystals. They were found in carbonaceous chondrites and in CV, CM, and the CO chondrites, which are characterized by aqueous alteration processes. And besides that, it was found as micrometeorites, but micrometeorites experienced oxidation of metal during atmospheric entry, so no chance for some similarity. But comparing to carbonaceous chondrites, these tiny crystals do not exceed 10 microns, and it's very small because we have, if we have spheral, it's 100 of microns. And now we start searching for the grains in the terrestrial environment, and we have found that similar magnetites can form in pneumatolytic hydrothermal processes on the Earth. This is magnetite spheral from volcanic aerosol from Tolbachik eruption, and you see this similar triangular texture and the hole inside. And it was found in hydrothermal porous magnetite ores of volcanic province El Laco in Chile, and the size of such forms is already 1 millimeters, quite a lot. And the authors of this paper, they suggested that these large spherules could be formed during prolonged infiltration of the iron-bearing fluid. So we suggested, could it be some fumarole activity on the moon in the landing site? And everybody knows this famous Apollo 16 sample with name Rusty Rock, and it contains iron metal, which is surrounded by rims containing troilite, phases of iron and zinc sulfide and chloride, and their alteration products. And experimentally it was shown that iron metal reacted with fluid containing carbon, oxygen, sulfur and chlorine at 600 degrees. It means that fumarolic activity is possible on the moon. We start searching something else, and we have found metal sulfide association, which is related not to the glass, not to the impact glass, but to the late stages minerals of the basalts. And the texture of the sulfide, of iron sulfide, suggests that it was formation from the gaseous phase. And it's also interesting that composition of this metal grains is, this is the distance 5 microns, and here we have iron with nickel, and here we have pure iron. And some concentration of nickel is observed. After that, we start searching something else, and we have found that it's not a single case. And we have found that troilite with this texture, with this special texture, it forms irregular shaped areas in the basaltic mesostasis. This is Fals-Skala maps, which and the colors corresponds to different elements. This is potassium, blue is potassium, yellow is phosphorus, and they are, and red is iron. Iron is red. And we see that all this sulfide mineralization is associated with late-stage mesostasis area of the basalts, and it means that it's not an impact, but this is a basaltic story. And this is my favorite fragment because it contains this sulfide, iron sulfide, and it also contains filamentous crystal of iron. And this one is a copper sulfide. As you see, the size of this grain is about one microns, and it's I don't know how to form this crystal in vacuum. Besides that, it has something like skeletal form. It means that the crystal grew at highly saturated environment with this copper. And it should be noted, these are spectrums, and it should be noted that copper is a trace element in lunar basalts, and it means it should be concentrated somehow. Some process, we need some process to concentrate this copper. And so we suggested that these features could be the evidence of the some type of fumarolic activity in Chang'e 5 basalts, and it happened at late magmatic or post-magmatic stages, and the evidences are the presence of magnetite from rhomboid-like crystal, textural evidences of the formation of iron, copper, and nickel sulfides and filamentous iron crystals from the gaseous phase, the relation of this association to the late-stage mesostasis area of the basalts, and low amount of sulfides in Chang'e 5 basalts. And if it happened, then afterward, during impact or impacts, this type of mineralization, was embedded into an impact glass. And that's all. Thank you very much.
Only one question.
Svetlana, have you found any traces of maybe Earth weathering on the regolith particles?
Not yet.
Ah, thanks.
It's rather
Thanks a
fresh.
lot. Thank God.
Okay, we have to start the next. So the next presentation will be given by Igor Sorokin, experimental data on the occurrence of and chemical composition of metallic iron nanospherules and comparison with data from the Chang'e 5 lunar soil.
Okay, hello everyone. I will speak about the experimental data and about preliminary data of the Chang'e 5. Also, I include data about Luna 20 lunar soil. So, the surface of Ariel's body usually conduct to the some spatial factors like a micrometeorite bombardment and irradiation of space of solar particles. So these factors are called space weathering. So here you can see the product of such factors of micrometeor bombardment. This is microcrater with fusion zone. Here you can see the splashes radiated from the crater, glass beads. And on the right, you can see another product of the space weathering is a nanophase iron. Now, this is photos from transmission electron microscope. And these particles, the spherules, found both in amorphous rims in lunar in regolith particles, and in the agglutinate particles. They dispersed in agglutinate particles. Agglutinate, it is a glass welded aggregate that includes fragments of the minerals and rocks. So there are two hypotheses of formation of such spherules of iron. The one uses the implanted solar wind hydrogen. So when the micrometeorite impact in the saturated with hydrogen particle, the iron oxide reduction to iron and water. So the second one is uses mechanism evaporation and condensation. So when as a result of micro impact, there occurs evaporation and iron oxide is stayed in vapor cloud. So then the reduction iron precipitate to the nearby grains. The reaction like this. Here you can see this process is illustrated on this scheme. Okay, so this is our experimental setup, and the laser is a good technique to simulate the micrometeorite bombardment. We use a millisecond neodymium pulse laser. Here on the left, you can see, the laser energy was 600-700 joules. This you can see the receiving chamber within air gas atmosphere, and we placed our samples inside this chamber. Inside this chamber, it was linen by copper foil. Here you can see the copper foil with a ejection products. And on the bottom of the slide, you can see the crater from the laser impact. Okay, the targets in our sample, in our experiment was basalt and basalt glass, peridotite, olivines with different iron content, two types of pyroxenes, anorthite and magnetite. And the main analysis technique was scanning electron microscope. Okay, here is a basalt crater, cross section of the basalt crater. The scheme of the cross section have here on the right. This is a like a profile of this crater. The diameter of the crater was 6 millimeters. And you can see here the bright zones. These zones of different chemical composition. This enriched in aluminium and calcium, and relative to the host glass, and depleted depleted to silicon and iron. So in these zones we are found the nanophase iron, these bright spots, the chains and scatterings of nanophase iron. It's need to notice and emphasize that we found these particles in the glass, these in depth about tens of microns. So here it is 50 microns. And we assume that these particles occur here in the melt, deep in the melt, and the main and since we don't have enough volatile reducing agents, so we assume that these iron nanoparticles occurs by thermal reduction in the melt. Okay, here the basalt in a plane, so to say, from above. Here is a crater and different zones of this crater with different zoom level. So you can see the morphology and texture of these nano or submicro particles. Here is a whole picture of the most of the whole picture. You can see the texture. The small bright spots is a nanophase iron. These iron particles, spherules. So in our experiment, we got the large particle up to few microns. And then we try to analyze it. We try to analyze the chemical composition. So a few words about methodology. So as I said, we got a large spherules enough to analyze by CEM, scanning electron microscope, by EDS, we use large for experimental data. We use large enough large spherules, about 1 microns. For the lunar soils, we use more than 600 nanometers. So here we analyze the not only nanospherules but the neighboring zones. We called it matrix. So we compare the content of the some elements in matrix and in the nanospherules. Here you can see the purple symbols. It's content in the matrix, in the glass. So this is the colored these colored symbols, the content in the iron particles, iron spherules. So and in the middle, it's we trap the matrix because this group of these spherules was less than 6 or 700 nanometers. So we use a low accelerating voltage to that's not to trap the matrix. And we measured composition of a total of more than 140 spherules. This in experimental and in the real data. This is a graph from the basalt glass. Here we can notice the spherules enriched in phosphorus and silicon. So there is a small of oxygen content. So we assume that the silicon in native form that include in iron spherules. Then this analysis for olivines. Here we can see that the spherules or particles of iron in olivine enriched in nickelum. So in this table you can see that the matrix content of the nickelum and in the spherules. And by the way, we can see that on this picture of the CEM picture that the simultaneous growth, recrystallizing of olivine microcrystals with iron particles. So it's morphology like a tooth, I don't know. So, and it's one of the proof that they crystallize in the melt. This chemical composition for pyroxenes. Here we can see another impurities in the phase iron. This is sulfur, chromium, nickel, and phosphorus. So okay, you can see these numbers in table and on these graphs. Some elements below the detection limit of the EDS in matrix, but we analyze it in spherules. This is a chemical composition for basalt glass. These two types of the basalt of the analysis is for spherules on the surface of the crater and in the cross section of the crater. So here we can see another impurities in nanophase iron. There's a silicon, phosphorus, nickel. Sometimes it's copper. And the original content you can see from the matrix and the enrichment in this section of table. Okay, a few nanospherules we conduct the transmission electron microscope study, and not only nickel and phosphorus enriched in the spherules, but the sulfur and the alkali elements. And a few words about the Luna 20 samples. The real lunar soil is the real lunar soil is more complex, and here we can see much more impurities in the big spherules. So this is zone of the agglutinate glass from the Luna 20 lunar soil. Here it is impurities, phosphorus, sulfur, cobaltum, nickel, and etc. And move on to Chaniya 5 lunar soil. This is a preliminary data. So here we can see this. We have a half of the milligram. It was we take it from the Committee of Terrestrial Matter in person of Svetlana Demidova. We grateful for her. And here you the observed picture of this sample. This so heterogeneous and fine-grained sample, heterogeneous in particle types and in chemical composition. So this just view of this sample. On the left, bottom left, you can see the chemical composition map. And on the right, you can see the some zones of the agglutinated glaze where we found chains of the nanophase iron. Then we using automated method, we calculate the size of 600 nanoparticles. Mean size was 40 nanometers. And here you can see the pictures of this nanophase iron. As I say, we use in our study just large ones, the largest. But unfortunately, the largest one was lower than 1 micron, and so sometimes we trap the matrix. So this is a semi-quantitative data of the analysis of such spherulas in Chang'e 5 lunar soil. We can see the some impurities in this nanophase iron, this natrium, a little bit nickelum, phosphorus, sulfur. The chemical heterogeneity of the lunar soil particles that undergo multiple transformations, multiple meltings, leads to chemical heterogeneity of iron spherulas. The larger spherulas act as a selective vacuum cleaner that traps the impurity elements of the original minerals and glasses. So silicon is possible impurity elements in the lunar soil. Alkali elements sometimes tends to increase in nanophase iron. It was a problem with Chang'e 5 lunar sample. The presence of topography made it difficult to quantify some results, some analysis for EDS method. And the conclusions. We assume the third possible mechanism of formation of metallic iron nanospherulas. So this is thermal reduction in the melt, and the laser technique is a good tool to investigate geochemical aspects of space weathering. We found some impurities in the large spherulas like nickelum, phosphorus, sulfur, silicon, cobalt, chromium, copper, and zircon. A more complex pattern is observed in the lunar soil due to multiple particle transformation. As I said, they melting and remelting, and include different types of minerals. And it's likely that the chemical composition of the large iron spherulas will affect the impurity composition of the minerals and glasses that have undergone melting. Thank you for your attention.
Any questions?
Hello. Thank you for your presentation. Okay. I have a question about the composition of the nanoparticle from the in Chang'e 5. Yeah, as you said, I think okay, for me, I think the amount of nickel and cobalt is a little bit high than our researchers. So my question is, what do you think of the results of the iron nanoparticle from meteorites or from the lunar basalts?
Sorry, I don't understand the question. It's so much words.
Yeah. Okay. Yeah. I mean, okay. Your report amount of nickel and cobalt is higher than Chinese researchers. Yeah, some more Chinese publications. So the high amount of nickel maybe is from meteorites. What do you think of the results of the nanoparticles?
Could someone translate it for me?
Yes, very good, very bad sound. If you will send us a message with your question, we shall consider.
Okay, okay, thank you. Okay.
About the nickel content. Okay, so we don't know exactly, but for example, when we compare with our experimental data, we don't have extraterrestrial materials, so the nickel enriched from the minerals, or for example basalt glass. In the real lunar soil, we don't know the source of this nickel, but we can propose that it from both sources, from the meteorites and from the some, for example, sulfides that was melted.
Yes, thank you. Yeah.
Okay. Have you found some convincing evidence of space weathering in the lunar regolith of Chang'e 5 so far?
In what?
No.
Yes, many of these almost all zones of that was analyzed. It was the space weathering products, the agglutinate glasses, or the nanophase iron is one of the product of this space weathering process. Okay.
Okay, more questions? No. We shall go on.
Okay, thank you very much.
Thank you. The next talk will be given by myself, Morphology of Impact-Induced Condensates, Lunar Findings and Experiment. Okay, I have pronounced the title of the presentation. So, vaporization and condensation is an intrinsic effect of high temperature processing of solids at all stages of the solar system evolution, from dust to meteorites and planets. So, vaporization and condensation used by hypervelocity impacts affect fundamentally the process of formation of solid material on growing planets. So, condensates have specific morphology and shifts in elemental composition and chemical structure compared to evaporated solids. Normally, condensates are enriched in volatile and depleting refractory elements compared to source material, and the Moon gives a unique opportunity to study impact-induced products due to their preservation at alias conditions. And the questions are how to distinguish impact-induced condensates from other volatile-rich findings, and what are the trends of impact-induced processing. So, it is normally we can find a lot of presence of such layers on lunar objects. For example, here is a droplet, glass droplet from Apollo 17, and it is easy to find such structures on the surface of the droplet, which is considered as the condensed layer. So analysis of Chenier 5 particle, for example, this one also shows the presence of such a condensed layer on the surface of this plagioclast cluster. You see here the empty holes which was covered by during the precipitation of the condensate layer. It was covered by some glasses, but then they were lost and it was a free surface. And also on Chenier 5, for example, this is about 20 micron particle, but if you go in a higher magnification, again you will find these mounds of this material which can be considered as the condensates. It is necessary to clarify that here is the impact graph. So during the impacts there is a pressure loading which goes along this Hugoniot curve, but then after the release of the pressure we comes to this two-phase region, and there is a solid material or melt which is going along this curve, and the condensate goes along this curve. So independent of what kind of impact it was, the melt goes here, and the the pressure, the vapor goes this way. I'm sorry. And here, this velocity is the velocity of the material after the shock wave, which is about half of the impacting velocity. So before the velocities of, say, 20 kilometers per second, we have partial vaporization. So that means that there is a melt which is boil off, and the vapor goes out of the melted impact melt, and immediately it starts vaporizing. So in one case of our experiments, we had a light gas, two-stage light gas gun. It is a camera to which the projectile comes at a speed around 6 kilometers per second. Then there is special grid system, the target, and here you can see the condensates which are collected under these grid systems. But it's a very, very, very difficult experiment, because the installation about half of this hole, and you collect only these 2 millimeter condensed plates. Nevertheless, the objects which are collected in these experiments, you see here these condensates which are just on the basalt blocks after the impact. And here is the lunar 16 regolith, which looks very, very similar with several dimensions of the condensed particles. But more easy and better to produce experiments with a laser pulse, which produce good condensates, which can form condensed layer, which is packed of these condensed particles, which are collected just on the foil, on the path of the flow of or the vapor from the target. These condensed particles depends on the material. So, for example, in experiments with augite, this is just normal silicate. They are true spheres, which are rounded and are collected in chains. But if we have volatile inside the target, for example, here is a anhydride. This is just a calcium sulfate, and the sulfur. You see here the same globules, but there is a sintering of the space between the globules, and there is a coral-like structures which appear. the particles, condensed particles, if with this TM image in experiment eodolite, yes, there is, for example, individual spherules, but you can see that they are more complex because there are internal structure inside these particles, and we still didn't investigate this effect. Most of the condensates from silicates are amorphous, and they don't show any structure inside, but there are several experiments with high temperature material which show that even the condensed particles, they can produce crystalline structure within these particles, and the shift of the chemical composition with these whether in impact experiments or in laser experiments show a certain trend in the towards the enrichment of volatile components. It was interesting to compare the morphology of condensed particles on the surface, for example, of Apollo spherules and in our experiments. Here it was, we called it a granular coating condensate, then there was areas of spherules which are packed as a monolayer. There is a dispersed globular condensate. Here is Apollo 15 spherules, and for example, here is a glass spherule in our experiment, and there is a highly dispersed. So, but it's more interesting to see this difference in the morphology of condensate, and we have a lot of volatile components. For example, here it was an experiment with a simulated comet, which was vaporized. It contained a lot of volatiles, sulfur, chlorine, and other phosphorus, and they are forming not typical spherules, but some rectangular condensed particles, which is very similar to these findings on the Apollo 17 spherule. It was also interesting to give the to measure the dimensions of these condensed particles. How uniform is this condensing mechanism for formation of condensed particles? Here is a comet simulation experiment which gives the mean dimension of condensed particles around 50 nanometers with minimum dimension 12 nanometers and the maximum about 120. It is very important for our point of view that there is a true threshold that we can easily see particles which are less than 10 nanometers, but we cannot find any particles which is less than 10 nanometers or 12 nanometers in this experiment. Here is the experiment with our jet. Again, this minimum dimension was about 16 nanometers and mean dimension about 50 nanometers. And this table gives some overview of these measurements, and this has different measurements from our experiments with comet simulation, experiments with Murchison with titanium basalt, which simulated the impact of the meteorite or carbonaceous chondrite into the lunar basalts, with augite, corundum, zircon, and with class of Chemie 5 and Apollo samples. But I want to say that there is a very small difference, and all the difference in the mean size is about 2. So from about 50, 55 to 20. So this shows that there was some uniform process, and minimum dimensions are also again around 10 millimeters to 20 millimeters, not millimeters, nanometers. And this is a case of the mechanics of vaporization and condensation, because condensation starts immediately in several free paths of molecules from the evaporated surface. They have immediately very high oversaturation, and the zone is immediately divided into the feeding zone for any particle, and then they are collected and form these particles. So the feeding zones, they cannot be different much, because this is some kind of physics. So we want to say that these dimensions are typical for impact vaporization. And conclusion. Some slides are lost, but I saved time. So laser pulse simulation of impact-induced vapor plumes is a gradual method for reproduction and investigation of resulting condensed material and the studied nanostructures on surface of lunar particles from collections of Luna 16, Apollo 15, 17, or Chang'e 5 have direct morphological similarities with condensate particles obtained in model experiments. This circumstance supports their evaporative condensation origin. While being deposited on surface of rocks, the condensates can form granular coating with various densities of or produce lumpy structures depending on the concentration of volatile components, and layers of condensate can fix sufficient quantity of volatiles. I lost the slide which shows that this layers it was possible to measure within these holes. When I show the Chang'e 5 condensed layer, the free surface and the surface with the condensate, it shows that this condensed layer is enriched in phosphorus, in sulfur. So I also have a very crude calculation that even this small surface, 20 to 10 micron, and thickness of about 50 nanometers, it has phosphorus, the quantity of phosphorus which is equivalent to apatite crystal about half millimeter large. So if we see that how many these condensed layers just on the surface of the regolith particles, we also can come to the conclusion that it's necessary also to consider the possibility to account these condensed layers as a storage for volatile elements, and this investigation deserve attention. So, in the dimensions of impact-induced siliceous condensed particles have Gaussian-like size distribution with minimum size not less than about 10 nanometers and the maximum size less than 200 nanometers. And larger particles are formed by coagulation of regular ones, which was also shown. Okay, thank you. Saved some time. Any questions? So I have to.
Thank you for a very interesting presentation. But you used only one type pulse laser, right? 10 - 3 seconds impulse. duration. What about another larger impulse, for example, microsecond, minus 6 or minus 9 nanosecond impulse? Why not?
Now, as I, if you use very short pulses, then you have to decrease the energy of the pulse because it is important to have a low power density. Otherwise, you cannot have pulses with power density higher than 10 to the 7 watts per square centimeter. Otherwise, there will be, because if you want to simulate impact expansion, impact-like expansion, it must be isotropic. More dense laser pulses provide not shock waves, it's the absorption of the energy inside the vapor cloud, and it will be overheated. It must be isentropic. Yes.
It's inside all fragments or only on surface all fragments? How
No.
they organized?
No, this deserves investigation, but I think that this is inside. And as I showed with some experiments with volatile rich touches, volatile components try to sinter inside between yes. Yeah, but then it is boiling. That it is evolution of material of condensates, and then it precipitates on the surfaces, and then it precipitates. This global structure precipitates first, and then between these globals there is a sintering of this volatile rich material, which gives these structures. I think it is three-dimensional. It's, I think it is interesting to investigate. I think that this is also interesting because now the water content is considered, people just try to calculate the amount of apatite crystals inside the basalt samples and recalculate the volume of this apatite with its water content to the water content in this sample. There are additional storages for volatiles. More questions? We can go. So the next talk will be given by Maxim Zaitsev, volatiles in the lunar regolith delivered by Chenye 5 mission, preliminary results.
Okay. So, good evening, dear colleagues. I'd like to present my talk about volatiles. And as for the introduction, during the previous missions, which were dozens of them, the samples of regolith from more than 10 areas of the moon were delivered to the Earth. The elemental and isotopic composition of the samples was determined and that gave a general idea of the lunar matter and the age of the matter. As for the composition of volatile components, it was also studied, but generally the lunar matter, the lunar regoliths and rocks is depleted in volatile components. And the early impression was that the moon is totally outgassed planetary body. Detailed investigation of lunar regolith samples and basalts provided valuable information on chemical composition and concentration of volatiles. As it was mentioned by previous presenters, the lunar regolith matter has been undergoing by complex processes, including space weathering and impact processing and etc. And the sources of volatiles in the lunar regoliths can be asteroids, comets, and interplanetary dust, emitting a variety of volatiles. And the source of hydrogen can be, for example, solar wind particles, which can be implanted inside the grains and give hydrogen. So as for external source of volatiles, the meteoritic matter and asteroidal matter also can be considered to be. So we got 2 samples of lunar regoliths delivered by Chang'e 5 mission, and the samples were received by IKI on February 3rd of 2023, and these are the main views of anti-collision packing boxes and some diagrams of sample containers. And as it was described in the documentation, the lunar sample should be stored in high purity nitrogen environment, and as terrestrial contamination can dramatically affect the any extraterrestrial sample, especially volatile poor samples. And from this point on, the special infrastructure was developed for the handling of the extraterrestrial samples in IKI. So parts of the infrastructure is shown in this slide. So we built a glove chamber with dedicated control systems using mass spectrometer for gas atmosphere purity monitoring, and also we used adsorption tubes for analysis of lower volatile organic impurities in the atmosphere of the chamber. So for that case we used this analytical complex for the analysis of the absorption tubes content. And also we we used some hermetic containers, dedicated hermetic containers for the storage and transportation of lunar regolith, and for the long-term storage of such material. So the initial containers were provided by GIHI, but they were modified here. So in this slide you can observe the test tube with original test tube with Chanyu 5 regolith sample, which it was opened in the glove chamber. So as for the experimental setup of our analysis, it's shown here. We used pyrolysis and mass spectrometric analysis for qualitative and quantitative analysis of volatiles. So the schematic diagram is shown here. So the material can be placed inside the quartz test tube, and can be placed, which can be hermetically sealed to the vacuum system and the mass spectrometer, and this procedure can be performed inside the glove chamber. So the material can be insulated from the effect of the terrestrial contamination. And so this is the main view of the setup. So, and you can see quartz test tube and this high temperature furnace and the test of this furnace. First we had to try to test our paralytical mass spectrometric setup on some artificial mixtures, and we used mixtures of partially dehydrated gypsum and calcium carbonate in CO2, which gives H2O, CO2 and SO2 at ppm level, and you can see some mass spectrograms here, and integral mass spectra below the mass spectrograms. So they reflects the volatiles coming out of the heating samples, heating gradually by with the rate of 50 degrees Celsius per minute. So in the initial mixture we can observe H2O and N2 and CO and CO2 and O2 release, SO2, and even some organics, and as we see in the other side of this slide, it's where the blank experiments result is shown. So the intensity of the same signals for blank experiment is lower, much lower than for the initial sample. And as for the other model samples, we used, for example, pulverized obsidian, which mass spectrograms are shown here, and we found water and CO2 and SO2 at ppm level in here, and quantified it. So also we examined a sample of tektite which was more depleted in water and SO2, but we also could observe this these substances in this sample. And in the summary, I could say that this experimental setup can be used for quantitative determination of volatile compounds, CO2, at least CO2, SO2, and H2O in the volatile pore materials, including lunar regoliths, at the ppm level and even lower levels, using milligrams of the materials. This method could be also considered as more representative for H2O analysis in the regolith than apatite-related determination by nanosims. But at the same time, PRMS is a destructive control method, and but after PRMS, at the same time, the residue of a sample can be used for bulk elemental analysis, except for some volatile elements. And as also volcanic glass, obsidian, and impact-derived material tektite are quite good analogies of volatile pore materials. And the setup for pyrolysis mass spectrometric analysis of volatiles was tested with volatile pore terrestrial analog and with some artificial mixtures. And this analysis of Soviet samples of Luna 16 regoliths are planned to be provided soon, and right after that Chanyo 5 bulk samples also will be analyzed. And we would like to acknowledge the China National Space Administration and the Russian Academy of Sciences and IKI administration, GeoHi also, the Committee on Extraterrestrial Matter of the Russian Academy of Sciences, and all the other scientists and engineers and technicians took part in our work. And thank you for your attention.
Questions?
Natalia Bizaeva, Vernadsky Institute RAS. My question is, which tektite did you use for your analysis? From which meteorite crater?
We
have this information.
As we considered that it could be the sample from
It can be Australian. Is it
from
tektite? Is it tektite?
Australasian tektites from the
yes.
No, this
Yes,
sample was
it was provided
donated
by Max Planck Institute for Chemistry
yes, long ago.
pretty long ago. So we
So you don't remember.
yeah. The former
Okay, but
institute,
maybe
yeah.
Sorry, but maybe it's from this crater. Perhaps.
Sorry, could you please repeat?
Yeah, I mean, from his institution, I mean, maybe the title is from this crater.
Maybe.
Yeah, perhaps.
По происхождению тектита.
Yes, it could be from the Rice impact crater. Yeah.
So my my question was about
Germany.
how about analyzing a collection of tektites for comparison. This might be an interesting side work from your work. Just an idea.
Okay. Thank you for your proposal. As for technique, we removed the crust from the tektite and opened the intact internal space, and then crushed it and pulverized it, and immediately passed it to the analysis. So it was not exposed to the terrestrial environment for really long. So
fresh, because there are different tektites, and we have now at the Vernadsky Institute we have a fresh collection of tektites from Chile that we acquired, and this is a new strong field, and we don't know the source crater yet, and this is we are working on that now, so
and
probably to be discussed.
Are they analyzed by some volatiles yet? No?
Not yet, not from our side, so this is to be done. And that's very interesting because we really need to find information about the source crater. This is a very broad discussion. This is a new tektite strewn field, so this might be interesting for collaboration.
Okay, thank you for your proposal. I think it could be a very very helpful cooperation.
More questions? Okay, we shall go forward.
Okay.
So
thank you.
The next talk will be given by Sergei Voropayev, Olivine Studies under Lunar Surface Conditions. Olivine.
Good evening, dear colleagues. So you are tired already, so I would try to speak shortly. And my presentation concerning olivine studies under lunar surface conditions, and it is collective work of a lot of people from the GIHI, and you can see later all devices which were developed. So motivation and goals of our study was to try to estimate what traces of water, gases, and volatiles can save on the surface after the mantle degassing and magma transport. So the very important questions appear. For example, how much water is stored in the main rock-forming minerals, silicates crystallizing from magma. How to determine the nature of possible source of water in the mantle based on nominally dry minerals. And in what forms will water appear on the surface of other planets after the release of a magma, for example, on the Moon or on the Mercury. And why olivine? Quite simple. Olivine is very popular in the solar system. It exists everywhere. So, for example, here on this picture, you can see the olivine basalt from the Moon collected by the crew from Apollo 15. The chemical composition here, it's a solid mixture, solid melt of the magnesium and iron, and nominally dry, so you cannot see here no traces of water in the crystal structure. And olivine occurs in the both mafic and ultramafic igneous rocks forming basalts. And in the mantle, it's about 50%. So it's the most abundant minerals on the Earth, but also on the Moon and Mars and other planets, as well as asteroids. For example, on Itokawa. So, and of course, now is a good question. Is Moon wet or dry? The old paradigm was the Moon is completely dry, but modern geochemical data indicate rather a wet lunar mantle in the past. For example, Saul in this Nature paper 2008 found a significant content of water up to 50 ppm in the lunar volcanic glass beds, and after that, another groups found content of water up to 1,400 ppm. So it's similar to the Earth basalts MORP. MORP is the mid-ocean Atlantic basalts, and it's a main rock of our ocean crust on the Earth. So also feldspars in lunar anorthosite were found to contain large amount of water, indicating a much higher water content in lunar magma and the lunar magmatic ocean initially. So the paradigm has shifted from an almost dry moon to a moon with a significant water content in the past. And of course, if you try to analyze volatiles which are saved in the olivine structure, you have to choose some degassing method. And we have chosen the gas chromatograph. So it's our Russian device, Crystal Lux from Yoshkar-Ola. Here you see the model. But the accuracy is quite enough. It's about ppm. And here you can see the technical details about the capillary columns, for example, temperature, working pressure, velocity of discharge, etc. And also here you can see the three main detectors and main gases which we have used. So it's mainly the hydrocarbons, hydrogen, nitrogen, methane, monoxide carbon, and water, of course. So, and crushed olivine grains in quartz boat with a volume about 3 microliter were placed in the reactor at the center of heater. System was locked with a vacuum stopper, and the closed system then purged about 3 hours in helium flux until no traces of atmospheric oxygen were detected on the gas chromatograph. Here you can see our device. So it's a general view, is a control panel, and it's quite simple. Here you can see the heating. Here is a quartz tube. Here is a small quartz boat with samples, and the helium flux is coming to the gas chromatograph. And here, of course, we have to choose some similar rock similar to moon basalts or moon olivine, just because the moon olivine is quite expensive. And here you can see, for instance, the Apollo 12 low titan basalts. It's a main oxides from silicon, titanium, etc. And here you can see the chemical compositions from the olivine and orthopyroxene from avachit. Avachit is the main ultramafic magmatic rock from Avacha volcano. And here you can see, for example, with olivine compositions, it's very similar to the low titanium basalts from Apollo 12. So we have choose the olivine from avachit, and just to try to analyze the limit of the accuracy of our devices. Here on the right side you can see the Avacha volcano. It's a home volcano of Petropavlovsk-Kamchatsky on Kamchatka. It's a very popular volcano where it's analyzed everywhere. Here in this paper you can see all details about petrology, mineralogy, chemical compositions of Avacha rocks. But most important, here you can see the chemical compositions of main rock-forming minerals from avachit, so olivine, clinopyroxene, orthopyroxene, and olivine is very similar to the moon olivine. And after degassing, so we have used the step heating degassing with interval of 15 minutes from 100 to 1100, And here you can see the water content and another gas content from the olivine from Avachit, for instance. And we know that the initial water content in melt was about 0.46%, but coefficient of distribution between melt and olivine of water is huge. So olivine, it's the push the water from his crystal structure. And here you can see only 180 ppm of water in the olivine, but also the hydrogen, nitrogen, and carbon dioxide. To compare with another conditions, we have used the olivine from kimberlite pipe, diamond pipe, Mir, where the magmatic rock is very dry. So gas fluid was extracted from the magmatic melt, and the rest is very low in water content, is about 0.03%. But again, we can see water about 12 ppm after degassing, but we can see no hydrogen, but a lot of nitrogen and a lot of carbon dioxide. So you can see that our device and our degassing method work quite well, and we have go to another method for more geochemical details about saved volatiles there. So in GeoChem, the Dr. Yelena Zharkova has developed under leadership of Professor Kadik and Lukanin the electrochemical cells. Here you can see the general view, and the main points is here is the two solid electrolyte cells. One is a standard, another is with sample, and after heating there is some potential difference between these two cells. And this difference is calibrated very well, and so we can measure the absolute value of oxygen fugacity in the olivine, for instance, or in pyroxene, or in anorthite. It's work quite good. And oxygen fugacity is quite important thermodynamical parameter, but it's shortly it's a ratio of hydrogen in the gas mixture of fluid, and it's and this parameter define the gas compositions, gas distribution in fluid. And usually in geochemistry, the people use the so-named buffer. Here you can see the buffer of CoFM. It's a quartz phyolite magnetite. Here is a magnesium-wüstite. And here you can see the partial value of oxygen. So here you can see, for instance, if we have reduced conditions, so the stable iron appear. And the olivine from Avachit, as you can see, its line trend is along with the magnesium-wüstite buffer. But for olivine from pipe Mir, you can see the clear difference. So this line is going more stiffer. So and it corresponds to the more reduced conditions of olivine from pipe Mir, and it's quite understandable just because the magmatic camera of this kimberlite pipe Mir is about 200 kilometers at least, and the magmatic camera for Avacha volcano and olivine from Avachit is about only 70 or 80 kilometers depth. So after that, we can calculate absolute value of oxygen fugacity, and after that go to the compositions of the fluid. And here you can see the results, for example, for olivine from pipe Mir and olivine from Avachit. Again, you can see the clear difference between the more reduced conditions for olivine from the pipe Mir. And again, it's quite understandable just because here you can see the boundary to the stable graphite, and of course you have the stable graphite just because you have a diamond there. So the result is quite understandable and logically presented. But after that, we have tried to use the infrared spectroscopy. We have infrared Fourier spectrometer from firma Simex Novosibirsk. It's FT. This model FT 801 with a lot of plugins. And again, you can see here the clear difference between the infrared spectra from two olivines. Here, for instance, you have it's olivine from Avachit. Here you can see the clusters, groups of hydroxyl groups. But by olivine from pipe mir, you can see only single hydroxyl group. And here you can see by pipe mir the traces of hydrocarbons. It's known. And here in this fingerprint region, you can see the traces or peaks from the silicon oxygen tetraeder. But again, after heating, we analyze the three different samples from the olivine from Avachit. So heated origin, black is original olivine, red is heating till to 600 Celsius, and green is heating till 800 Celsius. And again, here you can see by this transmission spectra clear difference. So it's a trace of serpentine here. Here also the trace of serpentine in olivine is serpentine as inclusion in olivine. But here you can see some additional peaks, and concerning ferrum oxide. But why ferrum oxide and which ferrum oxide? We have tried to use X-ray diffraction. We have at GIH the X-ray diffractometer Miniflex Rigaku Japan. It's very well. Work very well, and it's but the amount of this ferrum oxide was quite small, and we went into, here you can see any difference between the original olivine and heated till 1000 Celsius. No trace of magnetite, etc. But from another side, it's a good sign, just because the absence of magnetite, it's no oxidation by terrestrial oxygen, so we have no contamination from atmospheric air in our experiments, so it's okay. So after that, we use Raman spectroscopy. Raman spectroscopy is work very well for mineral compositions, just because the mineral with the same chemical composition, for example, arganite or calcite or diamond and graphite, chemical composition is the same, but Raman spectra quite different. So here you can see the olivine or phosphorate magnesium olivine phosphorate Raman spectra. Here is a typical double peak here in this region about 800 centimeters. And also here you can see the Raman spectra of hematite is ferrum trivalent oxide. Here is a characteristic peak about 1,300 centimeters. And after that, we compare two Raman spectra from the original olivine left and the olivine after heating right. And you can see here the clear peak of hematite. So possible redox reaction is here. Hydroxyl group oxidize two valent iron, and the hematite appear. But hematite is go to the surface, as you can see here. So here you can see the traces of the heating of olivine from Avachit from 300 to 1000. Here you can see the red color. It's a hematite, and for pipe mir is the same story. And of course, is hematite on the moon or not? Yes, hematite exists on the moon, and here you can see the map, remote sensing map from the Chandrayaan mineral mapper. And here you can see a huge region here in the north, to the north pole. It's a Mare Frigoris, Mare Imbrium, Mare Serentis. Here is amount or abundance of hematite here. So possible it was some heating event here, and this heating event of course heated olivine from this Mare basalts and produced a hematite surface, very thin surface layer, and now we can observe here by this mission. And after that, we try to make more theoretical investigations of possible forms of water in the olivine structure. We try to use hydroxyl with protium and hydroxyl groups with deuterium. So we used a package it's named Biomaterials Studio, and in this package you can introduce by hand the olivine structure with different hydroxyl group positions. After that the software calculate the stability of this structure, and after that the first step calculate the vibration frequencies, and the second and final stage calculate a lot of thermodynamical, thermophysical and optical properties of this artificial structure. For us it was very, very important to receive a reflectance index of Forster-Reed with embedded hydroxyl groups, and you can see here the results. So for example, the original Forster-Reed is a yellow line, is here, and Forster-Reed with embedded hydroxyl group is a green and red and blue here. And as you can see here in the from 500 and in this region, you can see almost no difference in the reflectance spectra. So it's the usual infrared region seems to be, you cannot analyze the water content in the olivine. But in this region is far infrared region, the difference is very, very big, very huge, and seems to be we have to move to a far infrared spectrometer for the remote sensing or local sensing on the moon. And I would like to say that this work was the last work with academician Marov. It's a famous scientist. He died unfortunately last year, but provided us with a lot of ideas, and we follow this idea till now. So thank you for your attention.
Questions?
You make a very strong point that olivine, lunar olivine is very similar to the Earth from Kamchatka. I have general question. Do you consider this as an argument in favor of this famous model of Eric Mikhailovich Galimov that of the formation of the Earth, of the Moon?
No. Unfortunately, no. But I know about the idea of Galimov. It's a very, very interesting idea. But the most important for us was the chemical compositions. So we choose precision chemical composition of olivine and rock, the same as the Mare basalt. That's it. Only this. But of course, if you receive the olivine from the lunar samples or from lunar meteorite, no problem. We can select water in this example. So we need only about 40 milligrams for analysis, and that's it. And it's not destruction. No. No. You are right, possibly. It's a very good question, but the very good question is the isotopic compositions of the water, of course. So we have to analyze what isotopic compositions first, and we will try now provide some isotopic installation in the GAHE to analyze this. Yes, right. So I can explain later. Thank you very much for you.
More questions? I have a question. Sergey. This is a trolley bus. Just coming back to the title of the presentation, olivine studies under lunar surface condition. What was the idea of lunar surface conditions?
Lunar surface condition is a vacuum.
Only vacuum.
Only vacuum. Only vacuum, and the heating. Yeah, that's it.
Yeah, but
No atmospheric, no gas mixture, no contamination, nothing in vacuum.
Yeah, but the range of heating was much higher than surface conditions.
No, why? It's from 200 till 1,000. It's nothing.
1,000. Okay, more questions? No. Okay, we shall
Thank you.
Go to the last talk of this subsession. The presentation by Lydia Lakhmanova, Spinel bearing lithologies in the Lunar Highland meteorites.
So, good evening, dear audience. My name is Lydia, and today I'd like to tell you about spinel-bearing lithologies in the Lunar Highland meteorites. In the last 10 years, the Moon Mineralogy Mapper aboard the Indian Chandrayaan first spacecraft detected regions rich in pink alumomagnesial spinel. It was found on both sides of the Moon and confined to large impact structures. It is important to notice that they are concentrated on the tops of central peaks and along the inner ring basins of large impact craters. So the authors of this discovery suggested that these deposits could represent a previously unknown lunar rock that they named pink spinel anaphysite, and it is characterized by a high content of alumomagnesial pure spinel, about 20–30%, and it is also dominated by mineral called plagioclase, or the glass with plagioclase composition. And the rock suggested not containing ferromagnesial minerals, silicates like olivine and pyroxene, which make the difference between all known lunar samples with spinel. And alumomagnesial spinel is a rare find among the lunar collection of mission samples and lunar meteorites, and it occurs mostly in two types of rocks. The first, called spinel troctolites. This is an olivine plagioclase rock. And the second, more uncommon rock is spinel cataclasites. They have a unique association, including minerals like spinel, aluminstatite, plagioclase, olivine, and they are considered to have a deep-seated origin. And traditionally, the compositions of spinels are shown on such spinel prism, and here you can see all the variations of the composition of this mineral, including ferrum and titanium-rich minerals, but we are interested in the bottom left corner with alumomagnesial spinel, and there are shown two fields. One of them is the composition of spinel from pink spinel troctolite, and the second, it is shown in blue square. This is the composition of spinels suggested by remote sensing, and as we can see, it is extremely magnesial and extremely aluminous. It has more than 95%. So spinel anaphysites are still a mystery to scientists if we make an assumption that they really exist. we have another question: how could such rocks have formed? And there are several major hypotheses for their petrogenesis. For example, assimilation of anaphysized by picritic-like magmas, the formation in the deep layers of the moon, and subsequent elevation to the surface. And the third is impact melt of troctolites. And in my report, I will focus on the last hypothesis. In our research, we focused on working with lunar collections, searching for this new lithology among the spinel-bearing rocks. As objects, we choose 3 different lunar highland meteorites, which are breccias. It is a type of rock containing many different lyric fragments brought together by impact processes. And in my research, I have studied polished sections by optical and electron microscopes. The meteorites are Dhofar 311, Dhofar 025, and NVA 11828, but during the study, it turned out that aluminomagnesial spinels are not observed in NVA. It contains only ferro and titanium-rich spinels. So, for this reason, we will not discuss NVA further. In Dhofar 025, we didn't find any rocks containing pink spinel. However, it is dominated by monomineral fragments in the matrix, and spinel has high aluminous and high magnesial composition. Their size varies from 10 to 20 microns, but one large crystal was found up to 70 microns. And it is important to notice that earlier here we found feldspathic impact glasses with spinel microliths. And spinel fragments have different textures. It can be rounded or clastic crystals, but the distinctive feature of this meteorite is the corona-like reaction. It is when it is reserved edges with corona rim, and the similar pictures was shown in the lunar meteorite NVA. You can see it on the left. So this structure can suggest that spinel can be dissolved in the matrix impact melt as a reaction with high temperature melt. And also in Dhofar 025, we have found a unique spinel bearing object with very unusual texture. We called it symplectite. This is an intergrowth spinel with mineral plagioclase and presumably with aluminstatite. And this texture is not typical for spinel, and it was found in some different lunar highland meteorites where efforts suggested the deep-seated origin of this association and texture. Well, the next meteorite, Dhofar 311, here we found one single fragment of spinel troctolite, so it's a rock containing spinel with igneous texture. Also, we see an olivine spinel intergrowth with idiomorphic, well-shaped crystals, and here are present monomineral fragments with rounded crystals. So here is the dependency graph magnesia to aluminous in spinels, and they are showing the probable source of this spinel-bearing rock. And as we can see, all the compositions of aluminum-magnesial spinel, they fit into the field of pink spinel troctolites. Some of examples are close to PSA, but there is no evidence of the presence of this lithology. The next part of our research was experimental study of the possibility of spinel anaphosite formation and a finding of impact glass with spinel microlith in the meteorite Dhofar 025 makes us to think about the third hypothesis about impact melt, and troctolites can be rocks considered as target rocks because they are widespread in the lunar highland regions of the moon. And according to this diagram, spinel can occur during the crystallization of melt with composition olivine and anorthite. So we decided to test this hypothesis and to make a lunar spinel anaphosite analog as a result of impact melt. We used four different mixtures with different proportions of olivine and anorthite. Here you can see the compositions, and our experimental conditions were the temperature 1400 degrees and the pressure 1 atmosphere. Our experiment lasted about 12 hours, and it was we used a high temperature furnace, and after we put our samples into the water, what we get as experimental products, we got glass with plagioclase composition with spinel crystals. And it's interesting to mention that in some areas they tend to cluster with each other. But if we look at the percentage of faces in the samples, we notice that the high spinel content in composition plagioclase 70 and olivine 30, and it's only about 13%, and it's much less than suggested by remote sensing 20 or 30%, and in other compositions they have even less content of spinel. So the conclusion that it doesn't repeat the characteristics of the orbital data, but it's close. And the conclusion of the report that fragments of pink spinel anaphosite predicted from orbital data haven't been found in the studied lunar highland meteorites, and the experiment suggested that this pink spinel anaphosite analog may be formed during impact melting of troctolites, but experimental products do not fully correspond to the predicted compositions from remote sensing. And lunar scientists from all over the world continue to search for this mysterious lithology, and the last data show us that they have found this pink spinel anaphosite. So this is the first detection, and we know that it could be a real rock. That's all. Thank you for your attention.
Thank you. Questions? I don't see hands. Thank you.
What if you consider, for example, higher temperature or change pressure, maybe you can obtain a higher yield of spinel? Could you consider changing of experimental setup in your future experiments?
Okay, please could you repeat your question? It's about experiment, yes?
Just last slide, yeah. Could you, if you change temperature and pressure for during your experiments, maybe you can obtain another result?
Yes, our conditions were temperature 1400 degrees and the pressure is 1 atmosphere. But frankly speaking, it's not strict lunar conditions because we have no buffer and there was the contact with atmosphere.
Okay.
Thank you. So now they are moving to a poster session and we will guide it by Igor Mitrofanov.
I want now to start our poster session. I want to start now our poster session. People who would like to participate in the poster session, please sit down. People who do not want to participate in the poster session, you may have your discussion outside. Professor Gerasimov, people who would like to discuss with you science, please. We want to start poster session. We are starting our poster session. Samples analysis bring to us 10 minutes delay. And if you want to finish at 7:45, we have to start immediately. I suggest that each presenter will be inside 3 minutes, including loading of the file. And for each announcement, I will tell you the next one, number 1, and the next one, number 2. So please be ready to keep our time. Lev Matveyevich Zeleный, we want to start our poster session. Thank you. Okay. The first presenter will be Johnson Ping with a preliminary ground optical polarization observation of the moon. Please, Dr. Ping, you may start. Do we have presentation of Dr. Ping? So we go on. The next presentation will be Alexander Basilevsky, and we have a good luck we see him. After Basilevsky, please be ready Feoktistova and Rodionova, and after Rodionova we will invite Yuri Nefedyev. So please, Professor Basilevsky, your presentation.
So, good evening. This is photogeologic analysis of shadow cam images of the permanently shadowed floor of lunar crater. It's me with two Chinese, Serezha Krasilnikov, one Chinese, and Yuan Li, another Chinese. Highlights. Surface morphology of the permanently shadowed floor and lower parts of inner slopes of the near polar crater Shoemaker was studied based on photogeological analysis of shadow cam images with resolution about 1.6 meters per pixel. It was found the surface morphology of the Shoemaker permanently shadowed floor is dominated with impact craters. Surface morphology of permanently shadowed parts of inner slopes of shadow of Shoemaker have wavy texture, often called elephant hide, that is typical for normally illuminated lunar surface slopes. And it was found specific morphologic type of craters having lobate rims, which probably is due to presence of H2O ice, of water ice in the target material. This is crater Shoemaker, red arrow, and this is 4 study areas, 1 and 2 on the floor, and 3 and 4 on the inner slope. And above is from our previous work, and below is this new shadow cam images. And this you see almost nothing, only above is previous work. It's just traces of orbit, and you see the elephant hide surface texture in the below images. And these are some lobate rim craters. You see they very specific in morphology. And conclusions, the above considerations confirm the of Basilevsky and Lee 2024 that the morphology of permanently shadowed floor of Shoemaker crater is dominated by small craters. We hope that future studies will allow to describe morphometry, especially depth to diameter of the cometer scale craters. Surface lower part of permanently shadowed inner slopes in Shoemaker has the elephant head texture, which is also typical for normally illuminated areas. The shadow cam images showed presence of lobate rim craters whose morphology is probably indicative of water ice of the target material. Thank you.
Alexander Tikhonich, thank you very much. Next presentation, Ekaterina Feoktistova and Zhanna Rodionova, the crater depths and the polar regions of the moon. Please, your time start.
Well, my presentation.
And after this presentation, we will listen Yuri Nefedyev. Please be ready.
Where is my presentation?
Ekaterina, we are waiting your presentation. Time is going.
I don't see my presentation on the.
Excuse me, Yuri Nefedyev, are you ready to present your presentation?
Yes, we are ready to present.
Please, I invite you to make your presentation now, and Ekaterina, we will give you opportunity to be next after Nefedyev. Please, Yuri, you may present.
Okay, my name is Alexey Andreev. Dear colleagues, I will represent a poster presentation called Creation of a Comprehensive Fundamental selenographic catalog of impact crater based on data from model lunar missions and satellite remote monitoring on behalf of Yuri Nefedyev as his co-author in this paper. It is well known that approximately 20% of the asteroids falling on the moon are slow ones, which means that their velocity during the impact does not exceed 20 kilometers per second. And in this case, up to 40% of the impactor's matter could remain in the subsurface layers. And according to the Lunar Reconnaissance Orbiter data, over a period of 7 years, a quarter of more than 200 new craters formed as a result of slow impacts with a velocity of about 10 kilometers per second. And in this picture, we may see the complex of Kazan Federal University main building and a crater of several hundred meters in diameter. And the areas of both of them are practically the same. So if we imagine that a slow impactor formed this crater and we can take mean values and about 20% of its matter remained on the surface, then we would be seeing about 20 tons of iron, about 3.6 tons of nickel, about 180 kilograms of cobalt, and about a kilogram of platinum as the fragments. And in this work, we were trying to construct a catalog of lunar impact craters using neural networks. To create a training sample, we used the images of the lunar surface from the Lunar Reconnaissance Orbiter, Kaguya, and Clementine space missions. And in this picture, we may see the training material drawn by hand, and based on it, the neural network learns to recognize an object in image. And we have to note that in this picture, the most typical craters are highlighted with clear rims. And in this picture, we may see a manually labeled fragment of the crater image on the left, and the one labeled by the neural network on the right. Obviously, at the moment, the neural network cannot recognize all the objects from the training sample in all cases, and it happens because of the undertraining. But more importantly, some objects that weren't in the training sample are recognized. This means that the model understands what it wants to learn. And in the future, it is necessary for us to increase the number of images to achieve a greater accuracy. And to sum up, the catalog that we have created is supposed to assess the possible content of useful resources on the moon by giving a clear answer to the question of what impactor, slow or fast, formed a certain crater. If it's a slow one, then up to 40% of the asteroid's matter could remain close to the boundaries of the crater. And in this case, this crater is suitable for extraction of useful resources. Thank you for your attention.
Yuri, thank you very much for your perfect time. So, Yekaterina, are you ready to present your talk about depths of polar regions, polar craters?
Yes, yes.
Okay, so I invite now to go to Yuri Bondarenko presentation about radar mapping of south polar regions at the 4.2 centimeter wavelengths. Yuri, are you ready to do your, okay, please go. And you are already loading. Please, after Bondarenko, we will invite Alexander Kosov. Okay.
Good evening to everyone. I will briefly tell about our work, radar mapping of the south polar region of the moon. This work is carried out under Russian Scientific Foundation support. So here you may find the main highlights of our work. we create new detailed radar maps of the South Pole region with about 75 meters per pixel spatial resolution. These maps were created using our radar observation at 4.2 centimeters. We prepare the maps with diffuse and specular as well as circular polarization ratio. Also on this map you can find the permanently shadowed regions which are not observable by optical instruments. All our maps we prepared on this website, so you may use it in your scientific work. So briefly, these instruments which we used in our radar observation. This is the principle of Doppler delay imaging. Then our image obtained in Doppler and delay coordinates, the radar scattering, and the examples of radar images which we obtain. After that, we prepare our own algorithm to tying the Doppler and delay to selenographic coordinates, and all of these maps we prepare on our website. So you may select on this website different radar maps and some other features on the moon. So for example, the scientists may use it for investigate permanently shadow regions, or for example the proposed landing sites. So thank you for attention.
Thank you very much. Please, Alexander Sergeyevich Kosov. The moon's gravity field investigation by the PKD instrument on the Luna 26 orbiter. Polina Savatieva, please be ready. Savatimova.
My report is moon investigation, moon's gravity field investigation by PKD instrument deployed on Luna 26 orbital. All authors, Kosov, Rashkov, Lev, Rashkov, Vladimir, are from IKI. The last successful experiment was conducted 2011. It was a GRAIL project from NASA. The results of experiment shown that the gravitational field on moon deviates from plus 500 milligauss to minus 200 milligauss. Its 1 gall is 1 centimeter per second square. So it is a objective of experiment is to measure really to repeat the experiment GRAIL, but something easy configuration and maybe improve accuracy. The layout of future experiment PKD is here. PKD experiment based on precise velocity and acceleration measurement between orbiter and ground station using Doppler frequency shift of reference Earth transmitter. Ground station irradiates monochromatic signal at Ka band frequency about 32 gigahertz, and transmitter power about 100 watts, antenna beam about 1/2 of degree or less. It needs about antenna 1 free diameter. Polarization is circular right. Specification of PKD instrument will be shown next slide. The PKD instrument consists of antenna and receiver. It's about 2 kilogram mass. The specification of PKD instrument is the next. Frequency, center of frequency is KK band about 32 gigahertz. Bandwidth of receiving signal about 1/2 of megahertz. Because of Doppler shift change about plus minus 200 kilohertz. Noise figure, noise temperature of receiver 150 K. Antenna beam width of instrument about plus minus 60 degrees. Most important parameter of the receiver is short-term frequency stability of internal reference source. For 1 second integration, we will use a reference source with stability about 10 power minus 13 10 power minus 13. It's allowed to its parameter depend from its parameter accuracy of measurement of acceleration of gravitational field depends. And we plan to have accuracy of gravitation field of acceleration of measurement about 3 power 10 power minus 3 centimeters per second. It is 3 milligal. It's accuracy of our measurement, of plant accuracy. It's compatible with accuracy of Grail experiment. And experiment will be conducted. It is possible when it will be possible to receive signal from reference source. It is possible to only at near side of moon. About 168 circle will be done during the experiment. Experiment duration will be about 14 Earth days. And during each circle, the measurement will be about 1 hour each circle because of time of full circle 2 hours. And each circle will be different from another about 1 degree, 1 degree at equator. At equator, 80 kilometers. At equator will be shifted each circle. So PKD will cover moon for about 14 Earth day, but information will could be received when moon is visible from ground station. To get full scanning, of moon. It needs to make additional scanning next 14 days.
Excuse me, I have to ask you to finish.
That's enough.
Thank you very much. Okay. Next presentation, Polina Savatimova will speak about next future mission to deliver polar ice to the Earth. Polina, please, another 3 minutes. And Alexandra Uvarova and Markovchuk, please be ready for next presentation.
Good evening, dear colleagues. My name is Polina Savatimova, and I'm going to present to you my report dedicated to application of cryo-cooling systems for the mission of lunar polar sample return. So, as you all know, it was discovered that there are quite extensive deposits of water ice on the moon's surface, and now it is a high interest to study its structure, how it occurred, and the possibility of detecting some biological compounds there. This direction of scientific development sets us the task to create a system that will allow us to return some samples of lunar regolith with water ice in it in unchanged state. So we have some parameters to develop such a system. The temperature of thermostating varies from 120 to 220 Kelvin. The lower temperature is the natural temperature of lunar regolith on moon surface, and the high temperature, 220 Kelvin, is temperature of ice recrystallization. At the temperature about minus 50 degrees Celsius, the structure of water ice is changing, and these changes can affect some potential inclusions that we can study later. So the weight of delivered sample is about 300 to 3,000 grams. The sample shapes is cylindrical, the residence time is 30 days, and temperature on board varies from minus 50 to plus 40 degrees per Celsius. So for sure, it is not a new idea to use some cooling systems in space, but previously developed devices were made to cool some detectors and sensors, and the idea of these sensors to work with semiconductors. So the temperature level for such systems is about dozens of kelvins, and it's a helium temperature level, but in our task we need to achieve a nitrogen temperature level and higher. Previously developed devices usually use Stirling cycle or Brayton cycle with different interpretations. Disadvantages of such systems is quite high power consumption, large mass, heat emissions, complicated construction, which can lead to ability of failure. Problem can be solved if we use systems based off liquid nitrogen receivers. Liquid nitrogen can provide us the temperature we need. Also, it's quite affordable and common refrigerant and source of cold. And these systems doesn't need electrical power, they doesn't emit heat, and they has quite a low weight. So already such systems are used on Earth. On the left side of the slide you can see such systems, scheme of such system which is already existing. Here the liquid nitrogen is cooling a sample. But still we need to compare passive cooling systems with active cooling system, because we cannot be sure that the liquid nitrogen will cool for all period we need. So while comparing these systems, we need to look at few criteria. The first is dependence of the mass of the system on the mass on the sample, also energy consumption and heat emissions, which equals 0 for passive cooling, also vibration operation, reliability, and which is the most important, capacity to work in microgravity or its full absence. So in future it is planned to conduct some research, compare several systems, and after that I hope we can choose the most optimal variant to cover all our aims. Thank you for your attention.
Thank you, Polina. Please, next presentation from Uvarova and Markovchuk. creation of soil analogs for scientific equipment testing. Do we have them ready? We do not have them online, so I suggest we go next presentation from Alexander Gusiev, infrastructure development of the Moon 9, 3D printing on lunar regolith. And Yekaterina Faber and Kaspransky, be ready for your next presentation after Gusiev.
It's, I would like to take for the short introduction of the 3D printing problem using for the lunar exploration now. Over the past decade, the China Lunar Exploration Program, CLEAP, as known as for the Chang Project C, has achieved novel, remarkable and important results. It has successfully developed and for the demonstrated for the engineering capabilities needed to reach and for the return astronaut from for the lunar surface. In particular, the project SE project achieved for the first over the landing and for the institute exploration of the far side of the moon and collected in the young volcanic core from the Precarium crypterranium. China and Russia lunar exploration plans included 3D printing building bricks from for the lunar soil. China intended the test of the printing bricks from the lunar soil in the coming years, which would for the major step towards establish a base of the moon. China is the current working in the next batch of the lunar mission, including Chang'e 6, which for the collected source sample from for the far side of the moon in June 2024, and for the multi-mission Chang'e 7 schedule of the launch in 2026, which for the source for the ice water in moon Chauvet crater 3. Chinese scientists confirm that the exploration, the possibility of the 3D printing building blocks from for the materials found in for the lunar surface. 3D printing in space lunar construction achievement has been for the construction and for the testing. You can see this picture concerning for the technological approach for the investigation lunar soil. This is techniques and for the this is achievement geological investigation now. 3D printing in the space lunar construction achieves has been considered and for the testing for many years. China, Russia, USA, and the European country are work on the producing lunar block from lunar regolith analogies. 3D printing for space activities has for the considered test for the many years. The European Space Agency is working to producing building bricks from for the lunar soil simulant, and for the Airbus is preparing to send the metal 3D printing to the ICCS. Yes. In 2022, USA firm for the Iconic received an additional $57 billion to the develop of the 3D printing system for the moon. This team up for the budget in this group and for the Source Plus to develop the donut-like ignolls with for the wave-like outer surface. The next test for the involved for the robotic arm and for the laser operating inside NASA thermal vacuum chamber which for the simulate the extremely cold heat and for the vacuum condition of the moon. The deep vacuum and the cheap solar energy open to the new horizon for the electronic foundries, metalwork, and the materials for the science of the moon. When it's coming to the large scale colonization of the moon and the Mars, 3D printing will be the use to build road and for the structure using their soul and for the regolith. I'm finished.
Thank you very much. Next presentation from Ekaterina Faber and Kaspransky about challenges and innovations of lunar environment simulation.
Good evening.
Do we have them? Okay, please, you start.
Okay. You hear me well, right? Could you hear me?
We can see your slides.
Okay, okay, but you hear me well, right?
Yes.
Okay, great. So I start with, I will not repeat what the previous speaker has already said, and the goal of my research is to begin to create a form of a future facility that would meet all the advanced technologies and the ability to conduct highly scientific research. So I will discuss the critical importance of accurately modeling lunar surface conditions as we prepare for future lunar missions, particularly in the light of the our Russian-Chinese agreement. And as we look forward to renewed human presence on the moon, understanding the lunar environment becomes paramount. And our research focused on various methodologies and technologies that help reproduce key factors of the lunar landscape. This include lunar terrain reconstruction, simulating lighting conditions, analyzing analog regolith composition, and addressing the effects of microgravity and health issues, and innovations in simulation technologies also discussing in our study with an emphasis on advanced aim at improving the accuracy and completeness of analog environments used for crew training and equipment testing for future missions. And by evaluating this modeling approach, the study aims to improve our understanding of the effectiveness of such projects in solving scientific problems, first of all, associated with lunar exploration. And the resulting data will help optimize analog facilities conditions and thereby increasing the readiness and safety of future cosmonaut missions. So this work is carried out on a fundamental basis and offers a look at need for long-term planning and development and creation new technology in the next 5-7 years for similar analog facilities. So the previous facilities and the missions, analog missions that we were conducting in the past was Sirius, Mars 500, Hera, Nemo, Caves, Chapea, Pangaea, Concordia. It's the main one. In the last, 1 month ago, in the Kern Delar facility, it's a European Space Agency was open lunar facility. You can see it on my slide. And this place is the biggest facility for today and the newest one. This large volume regolith simulant, it's about 700 meters squared, and is approximately 60 centimeter deep, filled with analog regolith, and with a lighting and camera system that will allow accurate 3D real-time position localization and to development and and we can use VR and AR technologies. And I want to talk about also one moment. Also about the goals, the key points, and I don't think that I have much time left. So for me, it's primary one is human factor research and training adaptation, educational programs that will lead to scientific research and the contributions to education initiatives and helps cosmonauts also adapt to stresses of the future missions. And it's need to keep in mind the scenario planning and sample collection strategies that will help us understand the terrain and environmental conditions on the real missions. So, in conclusion,
yes, Katerina, please, you have to conclude your presentation.
Okay. So, in conclusion, as we stand on the brink of a new era, we need to investigate these methodologies and thank you for your attention.
Okay, thank you very much. We are ready for next presentation by Olga Turchinskaya and Evgeny Sluta about landing site selection for Luna 27. Are you online? Okay.
Yes,
please
I'm online.
Use, yes, please, you may start.
One sec. I need to turn on my presentation.
And everybody, please try to speak louder because listening is not good in some cases.
Okay. Good evening, everyone. Today I will talk about the selection of the landing site for the Luna 27 mission. And this mission aims to study the lunar soil for water and other volatile components, which are key resources for future lunar exploration. Luna 27 is designed to land in a specific area of the moon's south pole. This area is highly challenging due to its terrain, where we encounter deep craters and steep slopes. The mission has to meet several technical and scientific requirements for a successful landing, such as safe slopes. Less than 10 degrees, the landing area should receive at least 35% of illumination, and more than 50% of the site should have visibility of Earth. We use data from LRO-NASA to map the terrain and assess slopes, illumination, and Earth visibility. As shown in Figure 2, 5 potential landing sites were identified based on these requirements. And then these sites were ranked with the addition of information about water content. Site 1 was selected as the most favorable due to its balance between safe slopes and high water equivalent hydrogen content. Other sites are our backup options. This slide shows the terrain characteristics of each land site. Figure 5 focused on the slope distribution across the sites. Table 1 shows that most of the terrain has slopes below 10 degrees, which ensures a safe landing. As you can see in Figure 6, the average solar illumination across these sites range from 37 to 41%. And Figure 7 highlights the Earth visibility, which reached up to 100% in some locations. These factors are critical for ensuring a stable power supply and communication with Earth. Table 2 provides a more detailed breakdown of these indicators for each site. The large scatter ellipse for ballistic landing limits the selection of suitable landing areas in this complex terrain. However, by improving landing accuracy and reducing the deviation to 0.5 kilometers, the number of potential landing areas that meet scientific criteria significantly increases, while still fulfilling the engineering safety requirements. This enables the Luna 27 mission to target areas with volatile concentrations of 0.2 to 0.3 weight percent in the central part of the sector. And that's all. Thank you for your attention.
Okay, thank you very much, Olga. Another landing site will be presented by Alexander Krasilnikov for Viper. As far as I know, Viper was not was reselected, but however, let us, if the talk is ready, let us listen. Please start.
Good evening. Now I present the results of the work done by me and my colleagues, the three-dimensional ecological model of the Viper mission landing area. Sorry. Viper mission is a NASA's project aimed at exploration of lunar polar volatiles. The Viper area is located on Mons Mouton, that flat top plateau that is near 100 kilometers across and 6 kilometers high. Mons Mouton is likely to represent a rim massif of the South Pole Aitken Basin, covered by younger deposits from nearby craters. Modeling of the subsurface geological structure of the mission area will provide important information for successful accomplishment of the mission goals. In our work, we produced the three-dimensional stratigraphic reconstruction of the Viper area using data of lower gridded topography, new geological map of the south circumpolar region of the Moon, and models of estimation of the ejecta thickness. For calculation of ejecta thickness, we use formula by Sharton, Hausen et al. And Fassett et al. For craters smaller 45 kilometers in diameter, 300 kilometers, and more 300 kilometers, respectively. As we developed the model, we construct a series of parallel geological cross-sections. They show the lower and upper limits of the stratigraphic units determined by the calculation of the ejecta thickness and defined by the local geological features. They reconstruct the three-dimensional structure of the landing area. We interpolated ejecta deposits of the same age between the nearest parallel cross-sections. As a result, it was found out that at the base of the Viper's cross-section, there are SPA basin deposits of uncertain thickness. The Amundsen-Gesven ejecta has a model thickness near 800 1,300 meters. The ejecta from remaining planetarium craters were combined into a single composite layer because it is impossible to determine the relative age of these craters. This composite layer consists of ejecta from craters Havers, Shoemaker, Malapert, Scott, Nobel, and 2 unnamed craters with a total model thickness near 250-500 meters. 3 craters in the study area could have penetrated through the composite layer of the pre-Nectarian craters and excavated Amundsen-Gesven material if their excavation depth is estimated as 1 to 10. The post-SPA deposits on a hill in southeast part of the studied area were affected by mass wasting processes and may be thinner. Thus, even smaller craters in this area may excavate the Amundsen basalt materials too. Because this material was excavated by the Amundsen basalt impact from the deeper horizons of the lunar crust, it has a very high scientific potential. Thank you.
Thank you very much. Alexander Safronov will speak us about lunar resources, the main goal which we take in mind when we go to the moon. Is it? Unfortunately, he is not online. So we go now to Vladimir Nazarov about Joint Lunar Data Center. Please, Vladimir. And our final talk will be about moon and gravitons. So people who are still here will be. Oh, it is announced that it will not be presented this last talk. So, Vladimir, you are the last one. The last one in our session. Good luck.
Anyway, we try to make it very quick, and main idea is just inform the community. Please come to us about our initiative. Its initiative is joint our initiative with our China's colleagues for creating the joint lunar data center, JLDC project. As you can see, it's very ambitious goals in our initiative, including to maximum possible scientific return, development of multi-purpose IT platform, preparation of new generation of scientists and engineers. This initiative was supported by China's National Space Administration and Roscosmos, and this project starts now. Main architecture is that it contains two main nodes, Russian and Chinese, and also some designated entities, some organizations, domestic organizations from both sides, which also participates in this joint center. Just a second. Very shortly, it includes 3 levels. It's built on base of a hierarchical 3-level model, which includes a technical level which covers basic equipment, practically computers, telecommunications facilities, very generous tools. Functional level, which includes mainly its special software, which for processing and analyzing the data, and expert level, which includes practically people, scientists, investigators, engineers. So from one hand, we can look on this system that it's expert teams, well equipped with enough computing facilities, and from other hand, we can look on it as a good computer information system equipped with respective support personnel. I'll skip some slides which describes the level to save the time. When it was preliminary design stage of this system of Russian segment, it was extended, so it's not only moon. Only moon was initially it was focused on moon investigations, but now it is extended, and a few organizations participate from Russian side in the system. You can see on the slide. So at the moment, it's practically covers, I would say, all directions, all areas of space researches. It's also some examples of what is now from China's part. Yes, yeah, yes. So what I will say at the end, the joint data center is not produced measurements. It collects measurement, I would say, from where it's possible, as from domestic missions, from joint missions, as from public researchers, and produce by their facilities, I'll say new technologies, which can be used for plans of future missions and as well as for operative plans during existing missions. And at the end, I would say just a few words that a lot of organization participates. It's not only T and China Space Agency. So door is open and look, someone.
Thank you for listening. If you have any questions, I hesitate to contact us by email. Thank you.
That's all.
Thank you very much. And we are finishing our Mercury and Moon session. It was a long day. We worked during 10 hours, of course, with the lunch 1 hour. But however, 10 hours was very, very, very good opportunity for us to present our results and our future visions. Thank you all very much. Have a good evening and actually have a good night.